Welcome to the Extraordinary 10 podcast, the place where the most magnificent and mind-bending facts in existence are explained to you in vivid detail.
It is fantastic to be back here with you.
Today, we are embarking on a massive journey. We've researched 10 extraordinary facts about the oceans. We aren't just giving you a list, we are diving deep into the science, the mystery, and the why behind these wonders.
And I have to say, looking at the research for this one, the sheer scale of what we're covering is going to completely change how you look at a map forever. It certainly did for me.
Absolutely. If you love exploring the unknown, don't forget to share this episode with a friend and subscribe to the channel. It's the best way to support the show and ensure you never miss a deep dive.
So should we jump in?
All right, are you ready to see the world differently? Let's start the clock. We're officially starting the clock. You might think you know the basics of this subject, but the reality is much bigger than you imagine. Let's start with the true scale. Fact number 10.
Fact number 10 is, I think, the fundamental truth that underpins almost everything else in marine science. It's this. The ocean is a single planet-spanning fluid shell.
Okay, let's unpack this immediately because I want to challenge that, right out of the gate.
Go for it.
When I look at a map or I spin a globe, I see very distinct names. I see the Atlantic, the Pacific, the Indian, the Arctic, the Southern Ocean. I mean, we grow up memorizing these as 5 separate buckets of water. Are you telling me that's scientifically wrong?
It's not wrong for, say, navigation or for culture, but physically.
Yeah, physically.
Right? It's basically an illusion. Those names, Atlantic, Pacific, they're just conventions. They're labels we put on the negative space between the continents. But if you look at the physics, the flow of energy, the biology, there are no walls. There are no borders.
So if I'm a fish, or I guess a water molecule, I just don't care about the lines on the map.
Exactly. You are swimming in one continuous global fluid envelope that wraps around the entire Earth. And the scale of this thing is, it's just hard to grasp.
Yeah.
We often hear that stat, that the ocean covers roughly 361 million square kilometers, or 71% of the Earth's surface.
Yeah, the blue planet stat we all learn in grade school. 71% of Earth is water. But I think that number can be, a little misleading.
How so?
It feels like a pie chart, 70% blue, 30% green. But we lose track of the actual, the volume, the depth.
We do. And the volume is staggering. It's somewhere between 1.33 and 1.37 billion cubic kilometers. But here's the comparison that I think really lands. It shows why the ocean is the dominant feature of our planet.
Okay.
Think about the land for a moment. Think about the highest mountains you know.
Everest, K2, the Alps.
Huge, right? But if you took a giant cosmic bulldozer and smoothed out all the land on Earth, knocked down the Himalayas, filled in all the valleys, the average elevation of all land above sea level is only about 840 meters.
Wait, really? Less than a kilometer?
Less than a kilometer.
That seems incredibly low. So
Yeah.
if you flatten the land, we're barely keeping our heads above water.
Exactly. Now, do the same thing for the ocean. Smooth out the trenches, the ridges, and the mean depth of this global shell is between 3,682 and 3,800 meters.
Wow. So on average, the ocean is more than 4 times deeper than the land is high?
Precisely. The continents are essentially just these thin, flat platforms barely poking their heads above the waterline, while the ocean is this massive, deep chasm surrounding them. The solid surface of our planet is mostly hidden under this single, connected saltwater layer.
It's wild to think that the continents are just islands poking out of this one massive system.
That's what they are.
But I have to push back a little bit on the physically one ocean idea, because the continents do get in the way, right? The Americas form a pretty solid wall between the Atlantic and Pacific. You can't just swim through Panama.
You can't know. The continents definitely block the surface flow in the middle latitudes.
Yeah.
But the ocean isn't just the surface. At the scale of fluid dynamics, all the basins are linked through these massive, deep gateways. Yes. Think about the bottom of the world. You have the Drake Passage between South America and Antarctica.
Right.
Then you've got the Indonesian through flow and the passages between the Atlantic and the Arctic. These aren't just gaps. They're the arteries of the planet.
The Drake Passage is famously the roughest water on Earth, isn't it?
The Furious 50s, yes.
Yeah.
And it's so rough because it's this massive funnel. It's the bottleneck where the Pacific and Atlantic can really crash into each other. But the connectivity goes even deeper than just water sloshing back and forth.
Yeah.
We can actually trace water masses moving across the entire globe.
Trace them how? You mean like putting a message in a bottle?
Sort of, but the bottle is the chemistry of the water itself. Oceanographers look at what are called temperature salinity signatures. TS signatures.
Sure.
For example, there's a very specific type of water called North Atlantic deep water. It forms way, way up in the Nordic and Labrador seas.
So way up north, it's got to be freezing cold.
Right. And the water there gets so cold and so salty that it becomes incredibly dense. And because it's so dense, it sinks. I mean, it drops like a stone to depths of 2,000 to 4,000 meters.
And it doesn't just sit there.
No, it starts a road trip.
A road trip.
A very, very long road trip. It travels the entire length of the Atlantic, rounds the tip of Africa, and circles into the Indian and then the Pacific basins.
That is incredible. So water that sank off the coast of Iceland could eventually end up deep in the Pacific Ocean.
Yes, but here's the kicker. It takes time. This whole global overturning circulation, it operates on timescales of centuries to millennia.
So if I'm looking at a wave in the Pacific today, some of that water might have last seen sunlight in the Atlantic while, I don't know, the Vikings were sailing.
That is a very distinct possibility.
Yeah.
We estimate the whole cycle takes about 1,000 years. So the water crashing on a beach in California today literally carries the chemical memory of the climate from the Middle Ages.
That really changes your perception of time, doesn't it? The ocean is on a completely different clock than we are.
It is. And because it's continuous, it means that energy travels through it like a single system, too. It's not just molecules moving, it's waves of energy.
You mean like tides?
Tides are a huge part of it, absolutely. Yeah. The gravitational pull of the moon and sun injects energy that propagates through this whole interconnected basin. It mixes layers thousands of miles away. But there are stranger waves, too. Have you ever heard of Rossby waves?
Rossby waves? That sounds like something out of sci-fi. Captain, we're being hit by a Rossby wave.
It does, doesn't it? But they're very real, and they're essential to understanding the ocean as one single body. They're what we call planetary waves. These are vast, slow undulations that happen because Earth is a rotating sphere.
How fast are we talking?
Huge. And unlike a surface wave at the beach, a barotropic Rossby wave feels the full depth of the water column. It moves the whole ocean, top to bottom. But they're slow.
How slow?
They could take years or even decades to cross an ocean basin.
Wait, hold on. A single wave that takes a decade to cross the ocean?
In a sense, yeah. They're not waves you could surf, so they're these subtle adjustments in sea level and pressure. But think about what that means. A disturbance, say a storm or a temperature anomaly on one side of the Pacific, can travel via these waves and impact the weather on the other side years later.
That really drives home the single system idea. You can't just poke the ocean in one spot without the ripples literally reaching everywhere else eventually.
Exactly. Even something like El Nino, which we tend to think of as a weather pattern in the tropical Pacific, involves these massive Kelvin and Rossby waves that traverse thousands of kilometers. They redistribute heat and they change rainfall patterns around the entire globe. It's all coupled.
So we've established it's huge, it's deep, and it's connected. But I want to talk about the shape of it, because you found this fascinating perspective in the research about the geometry of the ocean that, frankly, kind of unsettled me.
Ah, yes. The thin film perspective. This is one of my favorite ways to visualize it because it just completely breaks our intuition.
Correct.
We tend to think the ocean is incredibly deep because, 4 kilometers feels like an abyss to us as humans.
I mean, 4 kilometers is a long way. If I had to swim 4 kilometers down, I'd be dead. But it feels massive.
Well, ideally you wouldn't swim it, but let's look at it relative to the Earth itself. The Earth's mean radius is about 6,371 kilometers. The average ocean depth is, 3.7 kilometers?
Okay, doing the math, that's a tiny, tiny fraction.
It's less than 1,000th of the radius. To put that in perspective, if you scaled the Earth down to a smooth sphere with a radius of 1 meter, so like a big beach ball,
Okay.
the ocean would only be a few millimeters thick.
That is unnerving. It's just a damp film.
A thin film on a sphere. That is the correct physical description. I mean, if the Earth were the size of a billiard ball, the ocean would barely be a glaze of moisture. In fact, the Earth itself is actually smoother than a regulation billiard ball.
That sounds so fragile when you put it that way. Just a thin, cold, uniform skin on a rock.
It is fragile. And within that paper-thin film, the conditions are startlingly uniform. The density varies very, very little, only a few kilograms per cubic meter difference. And the temperature in the deep ocean is almost the same everywhere, mostly between -1 and 4 degrees Celsius.
So it's really just this cold, consistent shell.
And this is where it gets really interesting, because the planet is spinning. That thin skin is incredibly dynamic. The rotation, the Coriolis force, balances against pressure gradients to create this hugely complex three-dimensional circulation system.
I think we need to visualize this. I want you to really help our listener feel what it's like to be inside this thin shell, because numbers are one thing, but that experience is another.
Okay, let's do it. So close your eyes for a second, unless you're driving, of course. Imagine you're standing on the seafloor, middle of the Atlantic, 4 kilometers down.
Okay, I'm imagining it. It's dark.
It is absolute darkness. No sunlight has touched this spot for millions of years. The pressure against your suit is nearly 400 atmospheres.
Which is like having an elephant stand on your thumb.
Or a stack of cards pressing on every single inch of your body. It is crushing. But look up. Above you is this unbroken column of salt water reaching all the way to the surface. But here's the key realization. You are not in a lake. You're not in the pool. There are no walls.
That's the spooky part.
The water touching your faceplate is the same water that touches the shores of Antarctica, the beaches of Brazil, the cliffs of Ireland. If you could tag one single water molecule right in front of you, its journey would be epic.
Walk us through that journey. Where is it going?
It might drift westward, riding that deep conveyor belt we talked about. It travels through the darkness, enters the Southern Ocean, and swirls around Antarctica in the circumpolar current, the biggest current on Earth.
And then?
Then it branches off. Moves north into the Pacific. It slowly upwells. And eventually, maybe 1,000 years from now, it breaks the surface in the North Pacific. It finally feels the sun. Brief freedom. It evaporates, becomes water vapor, forms a cloud. It travels across Asia, driven by the trade winds, and maybe it falls as rain in the Indian Ocean and starts the whole cycle over again.
A 1,000-year commute. It's a planetary circulatory system.
It is. And while you're standing there in the dark, you'd feel something else. You'd sense those invisible waves we mentioned, that gravitational whisper of the moon and the sun flexing this entire fluid shell.
It's like it's breathing. The whole planet is breathing.
In a way, yes. A dynamic, pulsing shell.
This is great, but my brain is still struggling to reconcile the thinness with the complexity. You had an analogy in the notes that I really want to dig into, the honey on a basketball.
Yes. This is, I think, the best way to understand fluid dynamics on a sphere. Because when we say thin film, people think of, like, static water. But it's the viscosity and the spin that matters.
Okay, set the scene for us.
All right, picture an Olympic swimming pool. 50 meters long, 25 wide, 2 meters deep. That's a lot of water.
Huge. Millions of gallons.
Now, imagine we want to coat a basketball with a layer of water that's proportionally the same thickness as the ocean is to Earth.
Okay. How thick is the water on the basketball, then?
It would be the thickness of maybe a few sheets of paper. Barely a glaze.
Right. So we aren't dunking the ball, we're just misting it.
Exactly. Now, water runs off too fast to see anything. So imagine instead of water, we use honey. We spread a tablespoon of honey over that basketball to get that thin film. Now, you spin the basketball, say, once every 24 hours.
Okay, spinning the honey ball.
That honey isn't just going to sit there, right? The friction and the spin are going to start forming swirls, eddies, circulation cells, all driven by the spin.
And then we add the sun.
Right. Imagine heating the equator of the ball and cooling the poles. Now, the honey wants to flow from the warm parts to the cold parts, but the spin is deflecting it sideways.
So now the honey is flowing and swirling in all these complex patterns.
Exactly. And now imagine the honey is conductive, and it feels the pull of a moon orbiting nearby. Suddenly, that simple, paper-thin coating of honey becomes one of the most complex fluid dynamical systems in the universe.
That really helps. It's not about the depth, it's about the movement across the surface of the sphere.
Correct. A disturbance at one point on that basketball, you poke the honey, will eventually influence the flow on the exact opposite side of the ball, and that is our ocean.
This brings us to the so what part of this deep dive. Because this isn't just cool physics. This reality that it's one single fluid shell has huge implications for us as a species, doesn't it?
Oh, it changes everything about how we govern the planet, or at least how we should govern it.
Right, because our maps have lines on them. This is U.S. waters, this is French waters.
Sovereignty versus physics, that's the conflict. We have these concepts like international waters or exclusive economic zones. They're artificial constructs. We've imposed them on a medium that physically knows no division.
Pollution is the really obvious example here.
It's the classic tragedy of the commons. If plastic enters the water off the coast of Southeast Asia, it doesn't stay there. The ocean's circulation, that honey swirl, takes it everywhere. Microplastics have been found in the deepest trenches and in remote polar ice.
It becomes everyone's problem because the fluid just distributes it globally.
Exactly. It's like peeing in a swimming pool.
Ah.
You can't say, well, I only peed in the shallow end, so the deep end is fine.
A crude analogy, but it's accurate. The diffusion is inevitable.
But looking forward, the risks get even bigger. We're entering an era of deep-sea resource extraction and potential climate interventions.
Like geoengineering.
Yes, there's talk of ocean fertilization, where you dump iron into the sea to stimulate plankton to eat CO2. But if you do that in one spot, you're altering the chemistry of the single planet-spanning system.
We're not conducting isolated experiment.
No, we are tinkering with the life support system of the whole sphere. And because of those long time scales, that 1,000-year journey, the consequences might not fully unfold for centuries.
That is a heavy thought. We could be pulling a lever today that rings a bell in 500 years on the other side of the world.
That's exactly it. Our descendants will inherit whatever changes we inject into this system. Those changes will be carried along in that deep water circulation.
So what's the takeaway here? How do we wrap our heads around this?
I think the source material puts it beautifully. We need a radical reimagining of our relationship to the ocean. We have to stop seeing it as nations exploiting separate seas, my Atlantic, your Pacific.
And start seeing it as what?
As a single species responsible for the health of a single, irreplaceable fluid shell. There's no backup tank. This is it. The continuous nature of the ocean means we are all downstream from each other.
We are all downstream from each other. I like that. It makes you realize that stewardship isn't just about being nice to nature. It's about self-preservation in a closed loop.
Precisely. It brings us back to that astronaut perspective. When you see it from space, you don't see the borders, you just see the blue marble. Fact number 10 is simply the physics behind that view.
Well, I don't know about you, but I am never going to look at a beach the same way again. It's not the edge of the land. It's the beginning of the global shell that connects us all.
A shell that we are all floating in together.
That was Fact 10. Stay tuned. Fact 9 is coming up next. Welcome back. We are moving right along in our countdown. Let's dive into fact number 9. And this one is, well, it's the kind of fact that really challenges your whole perspective on where you live, what life on Earth actually means.
It really does. For most of us, life is green. It's solid ground. We live on the surface.
Exactly. But fact number 9 is this. The ocean dominates Earth's living volume.
And it's such an easy thing to overlook because our eyes are just trained on that 29% of the globe that's land.
We see the 71% blue, sure, but we think of it as a surface.
Right, but that's just surface area. The real measure, the thing that shows the ocean's true dominance, is three-dimensional. When you measure the habitable space on Earth, the biosphere.
The total volume where life can exist.
Precisely. The ocean provides more than 99% of that total space.
More than 99%. I mean, I had to read that a few times. That basically means that all terrestrial life that we ever see or talk about, every forest, every jungle, every single city, is crammed into less than 1% of the living room on this planet.
It is. And some analyses push that number even higher, up to something like 99.97%.
That's just wild.
The shocking volumetric reality. We focus on land because, well, that's where we evolved. It's easy for us to get to. But biologically speaking, land ecosystems are just a thin two-dimensional film wrapped around the Earth.
A veneer.
A veneer. The real biological machinery of this planet exists in the dark, cold, high-pressure liquid interior.
So our mission for this deep dive is to really unpack that systematically. How does the ocean achieve this incredible volumetric dominance? How does one single factor, depth, change the whole equation?
And crucially, why does it matter? Why should we care that we live on this tiny little sliver of space?
Exactly. Why is that 99% so important for our 1%?
Okay, so let's start with the basic architecture of life in these two places, land versus sea.
Yeah.
Because that's the core of the difference.
Right.
On land, the biologically active space is extremely confined. Life is basically pinned down by gravity, light, and soil.
So you have your soil layers, right? Maybe a few meters deep for roots and microbes if you're lucky. And then the trees, the canopy, that might reach up, what, a few tens of meters?
Exactly. Even if you count the thin layer of air where spores and things float around, the vertical space where life is dense is, it rarely exceeds a few kilometers. For the vast majority of biomass, the whole active zone is an incredibly narrow, compressed shell.
So terrestrial life is just sort of stretched out horizontally?
Precisely. Now contrast that architecture with the ocean. The biosphere in the ocean is the entire water column. It runs from the very surface, the air-sea interface, straight down to the deepest trenches.
Nearly 11 kilometers deep in some spots, like the Mariana Trench.
That's the one. And that depth, combined with that 71% surface coverage, is where you get the aha moment.
Let's talk scale then, because the ocean's average depth isn't trivial. It's not a shallow pond. It averages out to somewhere between 3.7 and 3.8 kilometers deep.
And when you multiply that average depth by the enormous surface area, you end up with a total water volume of roughly 1.33 billion cubic kilometers.
A billion cubic kilometers.
And here's the key. Virtually all of that massive volume hosts life. Microbial life, planktonic life. It's not just the surface, it's the whole stack, all the way down.
That difference in scale is what's so hard to visualize. We're used to walking horizontally. The source material had this great way of thinking about it.
Oh, the rainforest one.
Yeah. Picture yourself standing in the Amazon rainforest, one of the densest biological spots on the entire planet. You are surrounded by life, for sure, but it exists in a really narrow vertical band, maybe 60 meters tall, from the roots to the top of the canopy.
Now you have to mentally jump into the deep ocean. The scale just flips completely. Life exists in every direction, up, down, left, right, and it extends vertically by a factor of hundreds. Every single cubic meter around you has thousands, maybe millions of living cells in it.
So you're standing inside the living volume, not just on the floor of it.
You are. And that shift from a thin shell to this vast, dark, three-dimensional living space is what mathematically gets you to that 99% figure.
Okay, so let's explore what is actually living in that column. Let's start at the top, the layer that's still connected to the sun, the engine room.
Right, the sunlit part is the foundation. We call it the eusodic zone. It goes from the surface down to maybe 200 meters, give or take, depending on how clear the water is.
And this is where the phytoplankton live. The microscopic plants. I think a lot of us, we still associate oxygen production mainly with big forests on land.
And that's a totally understandable association, but it's an incomplete one. Because marine phytoplankton, even though they're microscopic, are estimated to produce something on the order of half of the world's net primary production.
Half.
And critically, they're responsible for about half of the oxygen that goes into the atmosphere. We always thank the rainforest for the air we breathe, but half of every single breath you take is courtesy of this invisible floating life in the top layer of the sea.
The planet's invisible engine. So productive, but it's only in a tiny slice of the ocean's total volume. So what happens below that, past that 200-meter mark where the sun just completely vanishes?
Well, now you're entering the deep ocean. First you have the mesopelagic zone, then the bathypelagic going down to 4,000 meters. These are dark, high-pressure realms, and they have these huge communities of bacteria, archaea, zooplankton. They're the deep-sea sanitation crew, really.
So the life down here isn't making new energy from the sun, it's just waiting on whatever falls from above, right? What scientists call marine snow.
Exactly. Marine snow. It's this constant rain of sinking organic, stuff-dead phytoplankton, fecal pellets, little bits of decay. And this is where the sheer volume of the ocean becomes so important. The organisms in these deep zones use that immense space to do one main job. They remineralize the sinking organic matter.
Okay, let's pause on that word, remineralize. For anyone who doesn't have a chemistry background, what does that mean in simple terms?
Of course. It just means they're breaking down the complex organic carbon, the stuff that was recently alive, back into its basic parts. Inorganic nutrients and dissolved carbon dioxide. They're recycling it.
So they're making sure the building blocks of life don't just get stuck at the bottom forever?
That's a perfect way to put it. And this massive recycling process is the core of something called the biological pump.
Right, it sounds very mechanical, a pump. How does the ocean's huge volume make this pump work to regulate the entire global climate?
The pump is basically a conveyor belt, and the volume is the storage container. Phytoplankton fix carbon at the surface. When they die or get eaten, that carbon starts to sink as marine snow. The deep water column is needed to catch and process all that snow. So the biological pump is just this process of moving carbon from the surface.
Or it could easily go back into the atmosphere.
And sequesters it, locks it away in the deep ocean.
So the massive volume means that carbon has a long, slow journey down. The deeper the ocean, the more time and space there is for all those microbes to do their recycling work.
Precisely. If the ocean were shallow, that carbon would cycle right back up very quickly. But the vast volume is filled with this active metabolism that regulates the global carbon cycle over hundreds, even thousands of years. It stabilizes the whole system.
And that already gives the ocean this overwhelming dominance, just with the water. 1.33 billion cubic kilometers of living space.
Yeah.
But this is where the numbers get, truly insane. We haven't even talked about the deep biosphere yet.
The life below the seafloor itself.
Yes, this is the part that is completely hidden, totally forgotten. The microbial life, the bacteria and archaea that are found down in the marine sediments and even in the oceanic crust.
And they extend hundreds, sometimes thousands of meters below the bottom of the sea.
I saw the estimates from the drill cores. The volume of this deep subterranean living world is somewhere in the range of 2 to 2.3 billion cubic kilometers.
Let that sink in.
That volume is roughly twice the volume of all the ocean water above it.
So when you combine the water column and the deep biosphere beneath it, the total habitable volume is over 3.6 billion cubic kilometers. Terrestrial life, by comparison, is almost a rounding error in terms of available space.
But it feels so counterintuitive. Life needs energy. The life in the deep biosphere, miles under the rock, isn't getting sunlight or marine snow, is it? It must be an incredibly low-energy place.
It is the ultimate slow-burn existence. This life exists at extremely low metabolic rates. Instead of feeding on sinking snow, they are sustained by these incredibly slow long-term processes. Things like diffusive transport and what scientists call redox gradients within the rock.
Okay, let's clarify that one too. Redox gradients. That sounds like high school chemistry. How does that sustain life in pitch black rock?
Think of it like a subterranean battery, a very, very slow one. Redox gradients just mean there are tiny differences in the electrical potential of chemicals in the rock and fluids.
So like chemical mismatches.
Exactly. These mismatches create tiny amounts of energy potential, and the microbes have evolved to harvest it. It's an unbelievably frugal way to live.
So they aren't reproducing every hour or day. Some of these cells might only divide once every few decades, or even millennia. It's not about being active, it's about sheer patient volume.
Right, and that immense, slow-moving biological reservoir is what dictates the planet's long-term functions. This connects back to the idea of residence time, what you called planetary memory.
Tell us more about how the ocean size gives it memory.
Well, the sheer size and depth create what we call long residence times. Think about a tiny mountain stream versus a massive deep lake.
The stream's water is replaced in seconds. The lakes might take years.
And the ocean is the ultimate reservoir. The typical overturning time for deep water, the time it takes for a bit of water to sink at the poles, travel across the globe at the bottom, and eventually return to the surface, is on the order of hundreds to over 1,000 years.
1,000 years. Meaning, if a huge amount of carbon gets transferred into the deep ocean today, it is effectively locked away for more than 10 human lifetimes.
Correct. The ocean's volume allows it to act as Earth's primary long-term storage unit and processing space for the critical biogeochemical cycles that regulate our planet. Land ecosystems are vital, but they're fast cycling. The ocean provides the long-term, slow-moving stability.
That really puts our surface-dwelling perspective in its place. Let's try to pull this all together with that powerful analogy from the source material, the one about the apartment building.
Right. If you imagine Earth's entire biosphere is one single building where all life lives.
The terrestrial part, the land, is like a sprawling but very low-ceiling ranch house. It's got a wide footprint, but the ceiling is only a few meters high. Maybe 60 meters if you include the tallest trees.
A very thin, compressed space.
But the ocean apartment, that's the real giant. It has twice the horizontal space of land, but instead of a 3-meter ceiling, its ceiling is 3,700 meters high on average. It's like a needle-thin skyscraper that stretches up more than 1,000 stories, filled entirely with living fluid.
And that analogy has to include the basement. The deep biosphere is the foundation. A massive, sprawling network of basements and tunnels that is twice as large as the skyscraper above it.
So most of Earth's living space is vertical, it's filled with water, and it's hidden in rock.
The message is pretty clear. When we think about life on Earth, we need to think less about the green forest on the skin and fundamentally more about the dark, pressurized, three-dimensional interior.
It's a very humbling shift in perspective.
Absolutely. The key takeaway here is that the overwhelming majority of Earth's habitable space, and probably its genetic and metabolic diversity too, is hidden away in this vast marine realm and its subsurface. We live on the geographic minority.
Which brings us to the big, provocative question this fact raises. If more than 99% of Earth's habitable volume is in the ocean, and there's life pretty much all the way through it, why do humans know so incredibly little about it?
It is a profound irony, isn't it? We have these huge systems dedicated to looking for life on other planets, but we've mapped the surface of Mars in higher resolution than our own seafloor.
Why, though? Just because it's hard.
It's incredibly hard and expensive. The pressure is immense, it's totally dark, and the deep biosphere, miles beneath the seafloor, is even harder to get to.
So we have to ask you, the listener, this question. Are we ignoring the majority of our own planet's biosphere just because it's inconvenient? What might we be missing? I mean, entirely new ecosystems, unique biochemical pathways, life strategies we can't even imagine. By ignoring the 99%, we might be missing the key to stability and genetic wealth right here on our own planet. That covers 9.
Ready for the next one? Let's head to fact 8. Welcome back. We are moving right along in our countdown. Let's dive into fact number 8.
And this fact, I think, really shifts our perspective on the planet itself. We spend so much of our time talking about, the surface, the land, the coastlines.
The parts we see.
Exactly, the parts we live on. But fact 8 forces us to confront this absolutely massive volume of our world that is, for all intents and purposes, an alien environment.
It really is. So fact 8, the deep ocean is a high-pressure, cold, planet-scale abyss. And our mission for this deep dive is to get past that simple idea of depth and really explore the physics. We're talking about crushing pressure, the extreme cold, and the incredible challenges both for engineering and for life itself.
And the scale is it's hard to wrap your head around.
Right. We say it covers 2/3 of the planet's surface area, but you have to think about that vertically. It's a colossal volume.
It truly is. If you could magically remove all the water, you'd see that the continents are just these relatively small high points on a planet that is mostly deep basins. The deep ocean is the default state of Earth's surface.
Okay, so let's define our terms first. Where does this abyss actually begin? It's not right off the beach, I assume?
No, not at all. The official boundary, where we say the deep pelagic realm starts, is all about sunlight. It's the point where there's no more usable light for photosynthesis.
The aphotic zone.
The aphotic zone, exactly. That threshold is usually around 200 meters down. Below that, you're in a state of permanent planet-wide night. It's always midnight.
And 200 meters, that's deep. But it's not impossibly deep for a trained scuba diver. It's wild to think that just below that, everything changes completely.
It's a fundamental switch. And from there, it just goes down and down and down. The average depth of the entire global ocean is somewhere between 3,700 and 3,800 meters.
So almost 4 kilometers on average.
4 kilometers deep, pretty much everywhere. For context, that's 4 times the average height of all the land on Earth.
So if you took all the mountains and plains and just dropped them into the ocean, you'd still have this huge amount of water covering them.
A huge amount. And then, of course, you have the extremes, the part that always captures the imagination.
The Mariana Trench.
Challenger depth, specifically. The latest measurements put it at about 10,920 meters, nearly 11 kilometers straight down.
Wow.
It's a depth so profound that if you put Mount Everest on the bottom, its summit would still be more than a mile beneath the waves. But whether you're at that average depth or the very bottom, the one thing that defines everything is the physics of hydrostatic pressure.
Okay, this is where it gets really interesting. Because 11 kilometers of water is a number, but what does that actually mean? What did that force feel like?
Well, the basic principle is surprisingly simple, and it's relentless. For every 10 meters you descend, the pressure increases by 1 atmosphere.
So 1 atmosphere being what we're feeling right now, just sitting here.
Exactly, the weight of all the air above us. So you go down just 10 meters, and you've doubled the pressure. You've added the entire weight of the atmosphere all over again.
And that just stacks up incredibly fast. It's not just water, it's the cumulative weight of all that water.
It accelerates like crazy.
Yeah.
So at that average depth, 3,800 meters, you're looking at a pressure of around 380 atmospheres.
380 times the pressure on the surface.
Yes, and just to frame that, when your ears pop on an airplane, that's a tiny fraction of 1 atmosphere change. This is hundreds of times that on every square inch of your body.
And that's just the average.
That's just the average. Take it all the way down to Challenger Deep, and the pressure hits about 1,100 atmospheres. A force so intense it actually compresses the water molecules themselves. The water at the bottom is about 1.8% denser than the water at the top.
So the ocean is literally squashing itself under its own weight.
The ultimate squeeze. And here's an analogy to help you visualize that force. Imagine a 1 square meter plate on the hull of a submarine down there. At 1,100 atmospheres, The force on that single square meter is equal to the weight of tens of thousands of metric tons.
Tens of thousands of tons. That's not a few cars. That's like stacking dozens of jumbo jets on a dining table.
It's an all-encompassing, crushing force. And that right there is why human exploration is so hard. Conventional submarines, even military ones, are limited to a few hundred meters, maybe 1,000 at the absolute extreme.
The engineering to go deeper must be just on another level. Can't have any weaknesses.
None. Zero margin for error. We're talking exotic titanium alloys, perfectly spherical ceramic hulls. A single microscopic flaw, a tiny crack, would lead to an instantaneous, violent implosion.
Which is why we mostly send robots.
Exactly. ROVs, autonomous platforms. They don't need a life support system, and if they fail, it's a financial loss, not a human one.
I remember hearing about that plastic bottle analogy. If you took an empty, sealed water bottle down to the bottom.
Oh, yeah. The air inside would be compressed to 1,000th of its surface volume. It would basically be crushed into a little plastic disc.
And yet, things live there.
Things thrive there. And that's the great biological paradox. How is that even possible when we would be turned into pulp instantly?
Right. My ears have trouble in a swimming pool. How is a snailfish just fine with 1,100 atmospheres of pressure?
Well, they play by a completely different set of biological rules. First, they don't have air pockets like lungs or swim bladders that can be crushed. Their bodies are mostly water, which is nearly incompressible, so they equalize internal and external pressure.
Okay, so they're not fighting the pressure, they're part of it.
Precisely. But the real magic is at the molecular level. They have these special molecules called piezolites that essentially protect their proteins and cell membranes. Our proteins would just unfold and stop working under that load. Theirs are built for it. They've evolved a chemistry that just shrugs at that weight.
It's a kind of biological engineering that's far beyond what we can do with metal and ceramics.
Way beyond it. The physics of the environment dictates the biology.
So we have this overwhelming pressure. What's the second big physical feature? The cold.
Yes, the cold. Once you get below the first few hundred meters, you pass a boundary called the thermocline, where the temperature plummets.
And below that?
Below that, the entire deep ocean becomes nearly isothermal, which means it's an incredibly stable, uniform temperature. And it's very, very cold. We're talking between -1 and 4 degrees Celsius.
So it's basically hovering right around the freezing point of seawater. Everywhere. All the time.
Pretty much. And that cold, combined with the salt in the water, the salinity is usually around 34 to 35 practical salinity units. That's the water's density.
So you get these layers of water based on how heavy they are. Denser water sinks.
Exactly. That's density stratification. And it's the key to understanding the deep ocean's very subtle, very slow dynamics. Even tiny changes in temperature or salt down there can create massive, slow-moving internal waves and eddies.
But if it's also cold and dense and stable, what makes it move at all? Why isn't it just a stagnant pool?
That's a great question. The motion is incredibly slow, but it's persistent. It's driven by a combination of things like tides and also the formation of sea ice at the pools, which makes surface water super salty and dense, causing it to sink. This feeds a massive, sluggish conveyor belt called the global overturning circulation.
The 1,000-year journey.
That's the one. But for that water to ever get back up, something has to mix it. And that brings us to the upwelling cycle.
How does that work? How does water at the bottom of the ocean get back to the top?
It all comes down to topography. So we all know about surface tides, the barotropic tides that make the sea level rise and fall.
Yeah.
When those massive movements of water flow over rough terrain on the seafloor, like a mountain range or the continental slope, that energy gets converted.
Into what?
Into internal waves. So instead of a wave on the surface, you get these huge, slow, rolling waves inside the ocean. They can be kilometers long and hundreds of meters high, and when those internal waves eventually break...
Like a wave breaking on a beach, but deep underwater?
Exactly like that. That braking action drives vertical mixing. It's the engine that slowly, gradually lifts that dense bottom water back up towards the surface, closing the loop of the circulation.
And the timescale for one full loop is just staggering.
On the order of 1,000 years, a water molecule that sinks in the North Atlantic today might not see sunlight again for a millennium, which means the deep ocean is like a planetary memory bank. It holds a 1,000-year record of the planet's heat and chemistry.
Okay, let's pull this all together. We have a world defined by impossible pressure, near freezing temperatures, total darkness, and a circulation system that operates on millennial timescales.
That's the abyss in a nutshell. And the scary part is, while we understand these basic physics, we know almost nothing about the biological and geological processes actually happening down there. You've heard the saying.
We know more about the surface of Mars than we do about our own seafloor.
And it's true. Which leads directly to the big question, doesn't it? The question of human intervention. If we don't understand it, what right do we have to start messing with it?
You're talking about deep sea mining.
It's the biggest threat, without a doubt. There's this huge push to go down there and strip mine the abyssal plains and hydrothermal vents for rare earth minerals, cobalt, copper.
With these giant robotic bulldozers and vacuums, essentially.
Yes, and the danger is directly tied to that timescale we just talked about. These are ecosystems where life moves in super slow motion. A deep-sea coral might take centuries to grow a few inches. Organisms on the plains live on such a limited food supply, their metabolism is incredibly slow.
So if you dredge up a section of that seafloor, it's not like a forest that can regrow in 50 years.
It might not regrow in 5,000 years. Or ever. We could be wiping out entire ecosystems that took millennia to evolve, and we have absolutely no baseline data to predict the consequences. We're basically planning to industrialize the largest biome on Earth while flying completely blind.
And beyond the direct destruction, we have to remember the deep ocean's role in the whole planetary system. It's not some isolated wasteland.
Not at all. It's the planet's single largest heat and carbon sink. It's our buffer. That slow, 1,000-year circulation has been absorbing the extra heat and carbon dioxide we've been pumping out, mitigating the worst effects of climate change at the surface.
For now.
For now. But if we disrupt that system, if we change its chemistry or its temperature, the consequences won't just be felt in a few years. They'll play out over the next 1,000 years. We are making decisions today that will affect the climate for 30 generations.
So the abyss is patient, cold, and dark. But it's not immune to our impact, and it seems like it might hold a 1,000-year grudge. But here's the thought for you to carry forward. Will humanity slow down, learn to respect and understand the abyss before we irreversibly damage it? Or will we repeat the same mistakes we've made everywhere else, exploit first and ask questions later when it's too late? The fate of the majority of our planet really does hang on that answer.
It's the last great frontier, and maybe our last chance to get it right.
That covers 8. Ready for the next one? Let's head to fact 7. Welcome back. We are moving right along in our countdown. Let's dive into fact number 7. Our mission today is to explore one of the most profound, yet often invisible components of Earth's climate system, the ocean's global thermohaline memory. When you think about climate stability, global warming, your mind usually jumps to the atmosphere, but we are going deep, literally miles below the surface, to see how the ocean archives information and well, what happens when we start writing disastrous, century-spanning data onto that massive planetary storage system?
That is a great way to frame it. That concept of thermohaline memory gets right to the heart of what governs deep ocean circulation. It sounds technical, but it's a beautifully simple term for a profoundly complex mechanism. Thermohaline just means the circulation is driven by differences in that's temperature, and haline, which is salinity or saltiness. These two variables, they're the master controls. They determine the water's density.
And density is the key here, isn't it? Because this circulation is essentially the planet's global conveyor belt. It's tasked with storing and transporting these immense quantities of heat, carbon, oxygen, nutrients. But it does so over truly vast timescales. We aren't talking weeks or years, we're talking centuries, millennia even, for a single cycle to complete.
Exactly. And what's so critical for you, the listener, to grasp is that this whole immense planet-enclosing system is driven by incredibly faint physical differences. It's not giant tides or, crashing waves. It's powered by small horizontal density gradients across the water column. It's a very finely structured system.
Right, and here's the speed paradox that I find so fascinating. We think of ocean currents as swift. The Gulf Stream, for instance, that moves really quickly. But in the deep interior, where this climate memory is stored, the speeds are often only about 1 centimeter per second. That truly is slower than a garden snail. Yet this flow manages to enclose the entire global ocean in a continuous 3-dimensional loop.
That patient persistence is the essence of its effectiveness. It's a very slow but very, very wide river.
I think we need to unpack that speed and scale contradiction. How is it even possible for a current moving at 1 centimeter per second to be responsible for transporting, 45 million cubic meters of water per second? That mass and that speed, they just seem wildly contradictory.
That's a fantastic question. It really forces us to appreciate the true scale of the deep ocean. So when you look at something like the Gulf Stream, it's fast, maybe a few meters per second, but it's geographically constrained. It's like a jet.
A narrow band.
A narrow band, exactly. The thermohaline circulation, on the other hand, specifically these massive deep water masses, they cover immense cross-sectional areas. Think of it less like a river and more like a continent-sized sheet of water, miles deep, just slowly, slowly flowing. So while the velocity is tiny, the sheer volume of water involved, the width and the depth, means the total mass transport is just colossal.
So the volume compensates for the agonizingly slow speed. Okay, that makes sense. Let's look at the engine room then. Where does all this cold, dense water actually begin its long journey down into the abyss?
It starts in the high latitudes, in a few very specific and very powerful zones. This is where surface waters undergo that critical transformation that they need to sink. You have the formation of what they call North Atlantic Deep Water, or NADW. That's primarily in the Nordic and Labrador Seas. But then you also have Antarctic Bottom Water, AABW, which is even colder and denser, and that's formed around the edges of Antarctica.
And what makes those specific spots so perfect for starting this whole global conveyor belt?
It's the combination of extreme cold and increased salinity. If you take the North Atlantic, for instance, you have these incredibly cold winds that just chill the water intensely.
Okay.
And crucially, as sea ice forms, it undergoes a process called brine rejection. When salt water freezes, the ice crystals push the salt out.
Oh.
So that increases the density of the remaining unfrozen water right there beneath the ice edge. This super chilled, highly saline water becomes so heavy it just cascades off the continental shelf and sinks all the way to the bottom.
Yeah.
And the AABW formation is even more extreme. It makes it the densest water mass on the entire planet.
And the sheer scale of this sinking process is it's difficult to visualize. The source material highlights formation rates for NADW at something like 15 to 20 million cubic meters per second.
It's huge, but the Southern Ocean overturning, which is the formation zone for AABW, is even larger. You're looking at 35 to 45 million cubic meters per second.
And to put that in context for you,
It's comparable to tens of Amazon rivers. Imagine tens of Amazon rivers worth of cold, dense water just sinking into the abyss at any given moment. That's not a trickle. That's a geological force that regulates global heat.
I think that's one of those scale numbers that we, as land dwellers, we just can't process. It really changes how you think about the planet's engineering entirely.
It truly does. And once those massive water masses form, they descend and then they follow these specific density layers. They hug the seafloor, spreading out toward the equator and into other basins. But this spreading isn't random. It's strictly guided by the ocean floor topography, the underwater mountains and trenches, and most importantly, the Coriolis force.
We've mentioned the Coriolis force before, but let's just make sure we define it in this context. Why is it so crucial for this slow, deep ocean movement?
Well, because we are on a massive spinning planet. The Coriolis force means that on Earth, fluids in motion don't travel in straight lines, they get deflected.
Right.
So in the northern hemisphere, these deep currents deflect to the right. In the southern hemisphere, they deflect to the left. This influence turns the flow into those immense slow-motion spirals and gyres that define the circulation pathways. It makes sure the water eventually reaches every corner of the global ocean.
Without it, the water would just pool near the poles.
It would just pool, exactly.
So once this water starts moving, pushed by density and steered by Coriolis, how long until it sees the surface and exchanges with the atmosphere again?
The residence times vary wildly. It really depends on which basin the water enters. Deep waters in the Atlantic are the quickest to ventilate. That means return to the surface and exchange gases with the atmosphere. Maybe within a few hundred years.
A few hundred years is the quickest.
That's the fast lane. However, if that parcel of water makes it all the way into the deep Pacific abyss, the residence time can be a millennium or more. And remember, the vertical motions, the actual return upward, are the slowest component of all. We're talking only a few meters per month.
A few meters per month, over thousands of kilometers of horizontal drift. That detail is what truly sells the idea of a deep-sea time capsule. Okay, let's shift our visualization now, because this is where the memory concept becomes real.
Absolutely. This is where we start reading the archive.
So imagine we could tag a single water molecule in the Labrador Sea on a frigid winter day, say in the year 1750. That's before the height of the Industrial Revolution, before massive fossil fuel use. So that molecule is a data packet. It's carrying the chemical signature of that specific pre-industrial era low atmospheric carbon dioxide, specific isotopic ratios, a certain temperature.
Right. And that molecule sinks 3 or 4 kilometers down, joining that massive current flowing at its snail's pace. For decades, then centuries, it just drifts along the bottom. It rounds the southern tip of Africa, snakes into the Indian Ocean, and then creeps its way across the entire breadth of the Pacific. The source material tells us this molecule could take a full millennium to finally upwell again. Maybe it surfaces near the coast of Japan, or in those powerful upwelling zones of the Southern Ocean.
And when it finally sees the light 1,000 years later, the world above has changed completely. The atmosphere is radically different. But that water molecule, that tiny data packet, still carries the faint, measurable memory of that long-ago 1750 winter in the North Atlantic. It's all encoded in its chemistry.
It's the ultimate slow-burn communication system. The sinking water acts like writing data to a very long-term storage system. Your hard drive analogy was perfect. When that polar water sinks, it's encoding the surface temperature, its salinity, its dissolved oxygen, and its specific QO content. The deep ocean is the vast archive.
And the retrieval time is measured in centuries, not seconds.
Exactly.
And the incredible thing is that scientists can actually read this archive today. They can determine its age and its history. How do they even do that when the water is 4 kilometers down?
It's logistically very difficult. It requires these massive research vessels, specialized sampling equipment. But the core process relies on what we call tracer chemicals. These chemicals act like timestamps. We use naturally occurring tracers like carbon-14, which decays over time, to determine the age of the water, how long it's been since it was last at the surface.
But the more modern, maybe more useful time marker is something we manufactured, isn't it? Chlorofluorocarbons, or CFCs?
They are the perfect industrial era time marker, yes. CFCs are synthetic chemicals. They simply didn't exist in the atmosphere until they were manufactured in the 1930s and 40s. So if we sample deep water today and find measurable concentrations of CFCs, we know precisely that that water must have sunk sometime after the 1940s.
And if there are no CFCs?
If the water has 0 CFCs, we know it sank before the industrial era. It's likely centuries, or even a millennium old.
That is profound. It means the thermohelian circulation is a long-term integrator of surface conditions. It gives the ocean this massive, enduring memory encoded in tracers that tell us not just what the temperature was, but when that water was last breathing the atmosphere.
And this capacity to archive is so critical, especially when we connect it to the bigger picture of modern climate challenges. We really need to focus on the Southern Ocean here, which the source describes as the critical hub of this entire global system.
Okay, so why is the Southern Ocean, that massive cold ring around Antarctica, why is it so important to this whole memory system?
Because it acts as the primary exchange zone. It's the most dynamic region for interfacing the deep ocean with the atmosphere. It's where deep, ancient water is forced to the surface, exchanges gases, and then subducted right back down. And it's shockingly efficient at its job.
How efficient are we talking?
The Southern Ocean accounts for a disproportionately large share of global ocean heat uptake, nearly twice its share of carbon uptake. It's uniquely structured because of the Antarctic circumpolar current and wind patterns that force this powerful upwelling. This process exposes ancient, cold, deep water to the modern atmosphere, and that water then efficiently absorbs both anthropogenic TROs and, critically, excess heat before being rapidly subducted back down into the global abyss. It's the planet's main pressure valve for climate change right now.
So the immediate, profound climate implication for us, the generation creating the heat in Koyero, is that the ocean is providing a massive, temporary buffer. The Koyeros, and especially the heat we are generating today, are being absorbed and transported deep into the ocean, sequestered for potentially hundreds of years. This process is helping slow the rate of atmospheric buildup today. It's keeping our surface climate from warming even faster than it already is.
That is the silver lining of the ocean's memory, yes. It buys us time, albeit at a cost. But there is a much darker implication here, which brings us back to that 1750 water molecule.
The climate debt.
Precisely. Even if all emissions stop tomorrow, the heat and carbon that are already written into the deep ocean, the data we've already archived over the past 150 years, that will eventually return to the surface through that slow, millennial-scale upwelling.
So the molecule that sank in 1750 will surface near Japan, maybe in 2750, carrying the faint memory of a pre-industrial world. But the water that sank in, say, 2024, carrying the intense signature of modern industrial heat, won't upwell until perhaps the year 3024.
That's absolutely right. Future generations are going to experience these delayed warming pulses and climate impacts that will continue to unfold over centuries, long after the original pollution source is gone. We are signing a massive intergenerational promissory note that our descendants will have to pay as that heat is finally released from storage.
It's an extraordinary legacy. And finally, the source raises a truly concerning point. Our activities aren't just changing the data written into the memory system. We are actively altering the conveyor belt itself. If climate change weakens the formation of North Atlantic deep water, say, by adding too much fresh water from melting ice, or if it shifts those Southern Ocean upwelling patterns, we risk fundamentally disabling the entire memory mechanism.
And if we fundamentally change the speed or the trajectory of this conveyor belt, we risk damaging the ocean's buffering capacity right when we need it most. The ocean is programming its long-term memory with current conditions, and that programming will persist long after we are gone. We are forcing a geological system to respond to a century-scale perturbation, and the system is showing signs of instability.
Which brings us back to the biggest question for you to consider. Are we inadvertently erasing or corrupting the ocean's memory system? What critical climate stability are we losing if we damage its capacity to regulate conditions over millennia? That covers 7. Ready for the next one? Let's head to fact 6. Welcome back. We're moving right along in our countdown. Let's dive into fact number 6.
Okay, so this fact, it really gets at a central paradox of our planet. When you look at a globe, you see the Southern Ocean, right?
That ring of water around Antarctica.
Exactly. And it only takes up about 30% of the total ocean area. But, and this is the whole point, its influence on our climate, on temperature, on ocean chemistry, it's just completely outsized.
And hunches way above its weight. And that's fact 6. The Southern Ocean is a global heat and carbon gatekeeper. So for this deep dive, our mission is to figure out how.
Yeah, how does this relatively narrow band of water act as the planet's most important control valve?
To gatekeepers, yeah. Managing this massive exchange of heat and carbon between the air we breathe and, well, the deep abyss.
It is the choke point. It's where the surface world, the part that's reacting to us in real time, connects to the deep ocean, which thinks in terms of centuries.
Okay, let's unpack this. Starting with the sheer scale of the currents involved, because the engine driving this entire system is immense.
It's almost hard to comprehend. We're talking about the Antarctic Circumpolar Current, the ACC.
The biggest current on Earth by far.
By far. And it's all powered by these incredibly strong, persistent westerly winds. You probably heard of them. The roaring 40s, the furious 50s, they just never stop.
And the unique thing about the ACC, the thing that makes it so powerful, is that there's nothing in its way, right?
Precisely. It flows completely unimpeded by any continents, no landmass to block it. So it just creates this continuous loop, this highway around the bottom of the world.
A highway that connects everything.
It links the Atlantic, the Indian, and the Pacific Oceans into one single global system.
So because it's unimpeded, the amount of water it moves is just staggering.
The numbers are, they're almost abstract. We're talking 100 to 150 million cubic meters of water per second.
Per second. And oceanographers have a term for this, sverdrups. And just through the Drake Passage, it's often over 130 sverdrups.
Yeah, and one sverdrup is 1 million cubic meters a second. It's a metric that's so big, it's basically useless for visualization.
So let's make it relatable. You have to give us that comparison from the source material. It's a good one.
Okay, so to get a handle on 130 sverdrups, I want you to picture the Amazon River, biggest river on the planet.
Right.
The ACC is moving about 500 times the flow of the Amazon River past the tip of South America every single second.
500 Amazons. Just wow.
Okay.
That's the scale.
But that's just the horizontal flow, right? The highway. The real gatekeeper part, the magic, is the vertical movement, the up and down.
That's it. That's the meridional overturning circulation. It's the complex plumbing system that's embedded within that massive current. It lets the ocean inhale and exhale.
And this is where the deep ocean finally meets the atmosphere.
It is. Those powerful winds we mentioned, they do something really interesting through a process called Ekman dynamics. They essentially pull the surface water apart. Wait, I have to stop you there because that sounds weird. Winds blows across the water horizontally. How does that make water come up from like a mile down?
It's a fantastic question. It's all about the Earth's rotation, the Coriolis effect. In the southern hemisphere, when the wind pushes the water, that force deflects it to the left.
Okay.
So the net effect is that the surface water moves away from the continent, outwards. It creates a physical gap at the surface, a divergence.
And nature abhors a vacuum.
So something has to fill that gap. And what fills it is this ancient, cold, dense water that's been locked away in the deep ocean for centuries. It's pulled up from below.
Pulled up along these density surfaces.
Isopycnals, yeah. Think of them as invisible layers in the ocean. The water just follows them right up to the surface.
So you get this water, which hasn't seen the sun in maybe 500 or 1,000 years.
Yeah.
And it suddenly surfaces near Antarctica.
It's a time capsule meeting the modern world.
And this is the planetary inhale. The moment it hits the surface, it starts to equilibrate. It tries to match the atmosphere today.
Exactly. It immediately starts absorbing modern anthropogenic carbon. And all that excess heat we've been pumping into the atmosphere.
It's taking on our burden. But it doesn't just stop there, which is why it's a gatekeeper and not just a sponge. It has to go back down.
That is the final, crucial step: subduction. This water is still incredibly cold, and processes like sea ice formation make it very salty, very dense.
So it sinks.
It sinks. It's now heavy with our modern heat and carbon, and it subducts back into the abyss as Antarctic bottom water or intermediate water. It exports that load for long-term storage.
That's the whole cycle. Bring up the clean ancient water, let it absorb our pollution, then sink it back down to hide it for centuries.
That's the gatekeeper function in a nutshell.
So let's talk numbers, because the sources are clear that the Southern Ocean is doing way more than its fair share of this work.
Oh, it's carrying a colossal burden. I mean, studies show it has taken up a huge fraction of all the excess heat from global warming and a very significant amount of our CO2 emissions.
And the really surprising part is the ratio between the two. The sources say it's taken up nearly twice the share of heat as it has of carbon. Why is it so much better at burying heat?
It's a great question. It seems to come down to the physics of the water masses. The density structure there is just hyper efficient at drawing heat down deep.
Huh.
The circulation and all these powerful eddies then spread that heat out, but they keep it trapped below the surface.
And that's the so what for you listening at home. This has two massive consequences. First, it slows down surface warming right there around Antarctica.
Which is why that area hasn't warmed as much as, say, the Arctic.
But second, it means all that heat is just being pushed somewhere else, warming the subsurface of the global ocean. The problem is hidden, not solved.
Let's use that house analogy from the source material because it's perfect. Imagine the Earth is a house that's overheating because of all the CO2 we've released.
Okay, the planetary thermostat is cranked way too high.
Right, and the Southern Ocean is this giant specialized air conditioning system.
But it's a weird AC unit. It doesn't actually cool the house by venting the heat outside.
No. It takes something like 30 or 40% of all the planet's excess heat, and it pumps it into a locked basement.
It hides it in the deep ocean.
It locks it away for centuries. And what that's done is it has fundamentally masked the severity of the climate crisis. The warming we feel at the surface is much less than it would be without this process.
It's been buying us time. But we know that system is changing. Models and observations are showing the overturning has actually intensified lately.
Yes, probably because of shifting winds, but the whole thing is balanced on a knife's edge. It's a battle between the wind-driven upwelling and the buoyancy-driven sinking.
And if that balance tips, the gate starts to fail.
Right. If the surface water gets too warm or if it gets fresher from melting ice, it gets less dense.
And lighter water doesn't want to sink.
It doesn't want to sink. The whole subduction part of the engine just weakens.
Which brings us to the really scary part, the big question from the sources. What happens when the gatekeeper fails?
Because its ability to store all that heat and carbon depends entirely on this delicate balance of wind, ice, and water density.
And climate change is attacking all three of those at once.
Exactly. Warmer water is less dense. Melting ice makes the water less salty, and therefore less dense. Shifting winds change the upwelling. The system is being stressed from every direction.
So, if the circulation weakens, the first thing that happens is that the Southern Ocean just stops absorbing as much heat and carbon.
Which is bad enough. That means warming on the surface and in the atmosphere immediately accelerates globally.
But there's a much worse scenario, isn't there?
There is a far more terrifying one. What if the upwelling of that old carbon-rich water continues, but the sinking of new carbon-loaded water slows down or stops?
The system reverses.
The entire system flips. It goes from being a net carbon sinker ally to being a net carbon source.
It starts work against us?
Actively against us. It would start releasing centuries of stored carbon back into the atmosphere on top of our own emissions. It is the absolute worst-case feedback loop.
A double whammy. We lose our planetary AC unit at the exact moment the basement door swings open and lets out all the heat and carbon it's been storing for centuries.
You've put it perfectly. It just underscores how critical these hidden oceanic processes are for keeping our planet stable.
The Southern Ocean has been our unwitting ally this whole time.
Quietly cleaning up our mess and buying us time we didn't even know we had.
So the urgency now is figuring out where that tipping point is. How close are we to overwhelming this gatekeeper before it turns on us?
That's the billion-dollar question. This isn't just some remote body of water. It is a planetary-scale control mechanism.
And it shows that a process happening in just one part of the world can have consequences for the entire globe for millennia.
Absolutely. Global consequences.
That covers 6. Ready for the next one? Let's head to fact 5. Welcome back. We are moving right along in our countdown. Let's dive into fact number 5.
And this one, for me, is just... It's probably one of the most astonishing things about how our planet works. We're talking about a secret, planet-spanning communication network.
A highway, really. An acoustic highway hidden in the ocean.
Exactly. It completely changes how you think about sound underwater.
Right. Most people, they imagine the ocean as this vast, chaotic place where sound just disappears, but this is the opposite.
It's incredibly structured.
So in this deep dive, we're getting into the physics of the SOFAR channel. That's SOFAR, for sound fixing and ranging.
And our sources all describe it as a fundamental part of global ocean physics, a natural waveguide that lets sound travel for thousands and thousands of kilometers.
An incredible distance.
Yeah.
So our mission today is to break down how the sound trap works, look at some of the proof, and then really get into the implications for marine life.
The life that has always depended on it.
Okay, so let's start with the basics. Where is this acoustic highway? How deep do you have to go to find it?
You have to go pretty deep. We're talking about the layer where the speed of sound is at its absolute minimum for that column of water.
And that depth varies.
It does, yeah. It changes with latitude, with the season. But generally speaking, in the mid-latitudes, you're looking at an axis that's around 800 to 1,000 meters down.
So a kilometer below the surface.
A kilometer down, way into the twilight zone, far beyond where sunlight can reach.
And why is that specific depth so magical for sound? I mean, normally, doesn't sound just get absorbed and muffled in water?
It does, and that's what makes it so counterintuitive. The reason sound can travel so far with so little loss is because of this physical tug-of-war.
A tug-of-war. Between what?
Between two opposing forces that control the speed of sound. Temperature and pressure. Hydrostatic pressure. The channel forms right where those two effects kind of balance each other out.
So it's not a coincidence. It's a specific outcome of deep ocean physics.
A very precise balance.
Okay, walk us through the mechanics of that, because this is where it gets really fascinating. How do temperature and pressure create this perfect trap?
Right. So first, you have to know that the speed of sound in seawater is usually somewhere between, say, 1,450 and 1,550 meters per second.
It's fast.
And that speed changes based on a few factors.
It does. It gets faster with higher temperature, higher salinity, and higher pressure. We can mostly ignore salinity here because it's pretty stable at these depths, so it really just comes down to temperature versus pressure.
Okay, so let's start above that 1,000-meter axis. What's the water like up there?
Well, above the axis, you're still in water that has some residual heat from the sunlit surface. It's warmer.
Ah.
And even though the pressure is lower, that warmth is the dominant effect. Warmer water means faster sound. So the speed is higher up there, maybe 510 meters per second, something like that.
So if a sound wave starts on the axis and tries to travel upwards into that warmer, faster layer, what happens? This is the genius of it. The wave enters that faster medium, and the laws of physics, specifically refraction, kick in. The wave gets bent.
Like light through a prism.
Exactly like that. It gets bent or refracted downwards, back toward that slower layer it came from. It's like hitting an invisible ceiling that just deflects it back down.
Okay, so that's the upper boundary. It's created by the warmer water. But what about below the axis? The water gets even colder down there, right?
Yeah.
So why doesn't the sound speed just keep dropping?
That's the critical part. And it's all about pressure. As you go deeper than 1,000 meters, yes, the water is getting colder, closer to freezing. Ordinarily, that would slow the sound down even more.
But it doesn't.
It doesn't, because the sheer weight of all the water above it, the hydrostatic pressure starts to take over. It becomes the dominant force.
We're talking about the crushing weight of a kilometer of ocean.
Immense pressure. Every 10 meters you descend, the pressure goes up by another atmosphere. It's enormous. And sound just travels faster under that kind of compression. The molecules are packed so tight that the energy transfers much more efficiently.
So the temperature is trying to slow it down, but the pressure is speeding it back up.
Precisely. The effect of increasing pressure wins out over the effect of decreasing temperature. So below the axis, the sound speed starts to increase again.
And if a sound wave tries to go down into that high-pressure, faster zone,
The exact same thing happens, just in reverse. It hits that faster medium and gets refracted back up towards the channel axis.
towards the point of minimum speed.
Always back to the point of minimum speed.
That is incredible. So it's a tunnel with no walls. The sound is just trapped there by physics. It can't hit the seafloor or the surface.
And that's key. The surface and the seabed are where you get all the scattering and absorption. That's what kills sound. But in this channel, it's protected from both.
The acoustic energy just stays focused along that axis.
Yeah, it minimizes what's called geometric spreading. Instead of spreading out in a sphere and getting weaker, it's forced to spread out more like a flat sheet horizontally. It holds its intensity for just vast distances.
It really is the ocean's fiber optic cable for sound.
That is the perfect analogy.
The idea that the ocean just, built this on its own is wild. So when did we first figure this out? When did we realize we could actually use this?
Well, the theory was developed back in the 1940s, but it was really exploited during the Cold War. The military, navies in particular, saw the potential immediately.
I'm guessing for submarine detection.
That was the big one, absolutely. Huge underwater microphone arrays, hydrophones, were installed on the seafloor just to listen in on this specific channel.
Makes sense.
But there were also some amazing humanitarian uses. They realized that if a plane went down or a ship sank, you could drop a small explosive charge set to go off in the channel.
A SOFAR bomb.
A SOFAR bomb, yeah. And that single pulse of sound would travel across the entire ocean basin and be picked up by those arrays, and you could triangulate the position of the wreck.
That's genuinely brilliant. Imagine being stranded and knowing your distress call could be heard thousands of miles away.
And today, the science has gotten way more sophisticated. We use something called ocean acoustic tomography.
Tomography, like a CT scan for the ocean.
That's basically it. Scientists set up controlled sound sources and receivers, sometimes on opposite sides of a continent. Then they send a sound pulse through the SOFAR channel and just time it very, very precisely.
Why do they do that? What does the travel time tell them?
It tells them the temperature of the water. Remember, sound speed is incredibly sensitive to temperature. So if a huge mass of water between the source and the receiver warms up even a tiny bit,
The pulse arrives a little bit faster.
a little bit faster, measurably so, and by analyzing those tiny changes across thousands of kilometers, they can build these incredibly detailed 3D maps of ocean currents and track large-scale climate warming across entire basins.
It's like having an X-ray of the deep ocean. So what's the proof of concept? What's the most extreme example of the range we're talking about?
The classic example from some of the early Navy experiments, they deployed a sound source in the SOFAR channel near Bermuda.
Okay, in the Atlantic.
In the Atlantic. And it was clearly detected by hydrophones off the coast of California.
Wait, California, that's over 5,000 kilometers away.
5,000 kilometers. That's roughly the distance from New York to London.
New York to London through an invisible underwater channel. That is just, it's hard to even picture. If you fired a cannon, the sound would be gone in a few kilometers.
It just highlights how unbelievably efficient this system is. But we have to remember, we didn't invent this channel, we just found it. The real users.
The original users.
They evolved with it. This is a biological superpower.
Let's talk about them, the great whales. I mean, the sperm whale is famous for its deep dives, right?
Yeah, exactly. Picture this. A sperm whale dives down to hunt squid. Right near that 1,000-meter axis, it lets out these powerful clicks for echolocation, for talking to its pod.
And because it's right inside the channel.
Those clicks are immediately trapped. They just race away at 1,500 meters per second, perfectly guided, losing almost no energy.
Wow.
And the really big whales, the blue whales and the fin whales, their calls are even better suited for it. Their low-frequency rumbles are just perfectly tuned to this channel.
So they can communicate over those same massive distances.
The science suggests, that a blue whale calling off the coast of Hawaii could be heard by another blue whale near Japan. The entire Pacific Ocean becomes their personal telephone line.
So their whole society, their mating, their navigation, their social bonds, it's all built on the fact that they have a 5,000-kilometer acoustic reach.
It is. Which brings us to the really serious part of this, the big implication.
Right. What happens when humanity decides to use that same channel as a sonic dumping ground?
That's the problem. Low-frequency noise, the constant hum of thousands of cargo ships, powerful naval sonars, the booms from seismic surveys for oil.
All of that sound energy is being pumped directly into this super efficient channel.
And because the channel is so efficient, our noise travels just as well as the whale calls do. And here's the critical conflict. The great whales evolved to communicate in the low-frequency bands.
Which is exactly where the noise from big ships is the loudest.
Precisely. It's not just noise, it's masking. It's like trying to have a whisper campaign during a rock concert. The shipping noise literally drowns out the biological signal.
It's just static.
It's worse than static. Some studies show that in high-traffic parts of the Atlantic, the background noise level in the SOFAR channel has gone up by 10 or even 20 decibels in just a few decades.
That may not sound like a lot to a person, but acoustically that's huge, isn't it?
It's massive. It means the effective communication range for a whale is just collapsing.
So if a whale used to be able to hear a potential mate from, say, 500 kilometers away, what's that range now?
It might be down to just 50 kilometers or less. We are acoustically isolating populations that used to be in constant contact across entire oceans. We're shrinking their world.
The really profound question here is, are we breaking their ability to find mates, to navigate, to keep their social groups together? We're running this massive uncontrolled experiment on a system we can't even see.
Filling their planetary highway with the constant grinding rumble of our economy. And because it's invisible, out of sight, out of mind, it just continues.
The SOFAR channel is a natural resource. It's a commons.
It is a vital acoustic pathway for life that has relied on it for millions of years. And the final challenge for us is to recognize that, to ask if these acoustic highways deserve protection for all the species that need sound to live in the dark.
That's a powerful thought. Your entire world, once spanning an ocean, is now just your local neighborhood. And you might be calling out, but no one can hear you anymore.
Indeed. We must reflect on the invisible nature of this acoustic pollution and the fact that we are filling a planetary communication channel that marine life relies on, often without realizing the extent of the disruption.
That covers 5. Ready for the next one? Let's head to fact 4. Welcome back. We are moving right along in our countdown. Let's dive into fact number 4.
This one, I think, really shifts our perspective. We so often talk about the ocean in terms of its physical motion, the currents, the tides, the waves.
The things you can see.
Exactly. But fact 4 asks us to look past all that surface turbulence and see something else entirely. It's about the chemical endurance of the planet itself.
Absolutely. The title is A Planet-Scale Chemical Reservoir with Million-Year Memory. And when you read that, you realize we're talking about timescales that completely dwarf human experience.
They do.
It suggests a level of stability that's, almost impossible to really grasp. This isn't just a body of water, it's Earth's massive chemical vault.
It is, and the surprising truth is that despite its just incomprehensible size, we're talking over 1 billion cubic kilometers, the ocean is a remarkably uniform chemical solution.
So it's the same everywhere.
Pretty much. It acts as Earth's primary chemical integrator, balancing all these chaotic inputs from rivers, volcanoes, the atmosphere, but it does it over geological ages.
1 million-year memory. That's not just stability, that's geological inertia.
Yeah.
But how does it actually do that? How can it maintain that near-perfect equilibrium when the water itself is moving so quickly?
And that's the paradox.
That's what we need to unpack here. This idea of fast movement, but incredibly slow change.
Precisely. So let's start with the basics, the chemical recipe. If you took 1 kilogram of seawater, you'd find on average about 35 grams of dissolved salts.
Okay, so that's the baseline salinity.
That's the baseline.
And what's crucial here, I think, is that the total amount might vary a little bit, like near a river mouth or in a hot evaporating sea, but the chemical mix itself stays constant.
That is the key insight. We are talking about the near constant relative proportions of the major ions by mass. You don't need to memorize the percentages, but you should know this. Chloride and sodium just dominate.
They're the two giants.
The two giants of the sea.
It's salt. I mean, plain and simple table salt. Chloride makes up about 55% of all dissolved mass, and sodium adds another, 30.6%?
Yeah, so right there you're at over 85% of all dissolved salts. Just those two elements.
And the rest.
The rest are these crucial buffering agents: sulfate, magnesium, calcium, and potassium. All the other trace elements, the ones that are often biologically active and get all the attention, they contribute less than 1% of the total.
That's amazing. To think that the water you dip your hand into in, say, Miami, has the same fundamental chemical composition as water sampled from a submersible near the Challenger Deep.
That global uniformity, where the mix is always the same, even if the total saltiness changes a bit, that's a rule so central to oceanography, we actually give it a name.
Which is?
Marseille's principle. It just states that the relative proportions of major ions are nearly constant everywhere in the open ocean.
I love that visualization from the source. Imagine those ions sparkling in the water, sodium as a pale yellow, chloride a shining green. And they're mixed with such perfect uniformity that every cubic meter you look at, whether it's deep or surface, polar or equatorial, is twinkling with the exact same constant proportions.
And that constant proportion, that leads us directly to the core paradox of Fact 4.
The timescales.
The profound difference in timescales. What's so fascinating here is the massive gap between the physical mixing time and the chemical residence time.
Right, the speed dial and the geological timer.
Exactly. The mixing time is, relatively speaking, fast. The entire global ocean is mixed by overturning circulation on the order of about 1,000 years.
So if I dropped a magical tracer into the North Atlantic, it would spread around the entire globe within a millennium.
A millennium, yes. But then you look at the residence times of those major ions, that's the average time an ion stays dissolved before a geological process removes it.
And we're not talking 1,000 years anymore.
No, we're talking millions of years. The numbers are just astronomical. Chloride, which is the most stable, remains in solution for approximately 100 million years.
100 million years. That's longer than the entire age of mammals on Earth.
It is. Sodium is close behind at about 68 million years.
Wait, okay, let me get the math straight on this. If it takes 1,000 years for the ocean to physically mix, but a chloride ion stays in the water for 100 million years, that means on average, that single ion has been circulated and mixed into every corner of the planet 100,000 times.
That's precisely the mechanism. Because these ions stick around for millions of years, they pass through tens of thousands of these mixing cycles.
Now,
that immense duration in the water is what guarantees they become so thoroughly homogenized, establishing that constant proportion that Marseille's principle describes. The physical movement is fast, but the chemical turnover, the actual change, is impossibly slow.
and even the slightly less stable major ions have these mind-boggling residence time. Magnesium and sulfate are around 10 million years, and calcium, which is the fastest of the majors to react, still stays dissolved for about 1 million years.
That stability is the key to life evolving in the sea.
So to make that distinction crystal clear, let's use that bank account analogy from the sources.
Oh, that's a good one, yeah.
We've got two currencies flowing through the ocean bank, and they're defined by their turnover speed.
Right, so first, you have your fast money. This is the reactive stuff trace elements like iron and aluminum, or, vital nutrients like nitrate and phosphate.
They have residence times of just decades to maybe hundreds of years.
Huh.
They get taken out of the system really quickly by things like biological uptake.
Right, where phytoplankton just grab them, or they get stuck onto particles and sink.
So they're like a constantly changing checking account balance. The balance just fluctuates wildly based on local sources. A dust storm over the Pacific, a river pouring nutrients into a coastal zone, a huge plankton bloom.
You take sample here and another one over there, and those fast money balances look completely different.
Then you have the slow money.
Our major ions. This is the massive trust fund that was established eons ago. Since they have millions of years of residence time, the balance barely changes.
And because the mixing is so effective over those vast periods, every bank branch, every ocean basin reports the exact same composition.
That account balance is guaranteed.
Okay, that trust fund analogy really works. But even a trust fund needs some careful management. If these ions are staying around for millions of years, what are the geological mechanisms, the sources and the sinks that keep the whole account from, overdrawing or running dry?
It's all about a perfect balance of fluxes over geologic time. The ocean's composition is shaped by continual inputs. Chiefly, that's riverine input from the weathering of rocks on land, atmospheric deposition, and also fluxes from deep-sea hydrothermal vents, where water reacts with hot rock.
And those inputs have to be perfectly balanced by the removal pathways, the sinks.
They are. The major removal pathways are things like mineral precipitation, sediment burial, and critically, the alteration of oceanic crust. where seawater chemically reacts with the rock at mid-ocean ridges.
So over geologic time, the system is designed to slowly self-correct.
Exactly.
And there's a really elegant example of that self-correction. The source is a key exception. Bicarbonate. Rivers deliver enormous amounts of bicarbonate, but in the ocean, it's only about 0.14% of the salt component. So why the small share, despite the huge source?
Because it has a very fast sink that rapidly balances that fast source. Bicarbonate is the fuel for life. It is quickly consumed by organisms to form carbonate minerals.
Shells, corals, skeletons.
All of it. So if bicarbonate didn't have that fast sink, the ocean would become supersaturated very, very quickly. You'd get massive, rapid precipitation, and it could destabilize the entire system.
So sodium and chloride accumulate because they just don't have a rapid removal pathway.
Exactly. That's why their residence times stretch to 100 million years. Bicarbonate, though, is removed very rapidly by life and chemistry, which keeps its proportion low, but also makes it critical to the ocean's carbon buffering capacity.
It's a fast-track reaction that maintains the stability of the whole slow-moving system.
It's an elegant balance.
And if we connect this to the bigger picture, we have to remember the ocean itself isn't one giant, instantly mixing tub. It's partitioned.
Correct. You have the upper ocean, which is a relatively small volume where all the air-sea exchange happens. The water here has a short residence time, maybe around 80 years.
And then you have the deep ocean, the vast, vast majority of the water.
Much, much larger. And that's the main bulk of the reservoir, with a typical water residence time closer to 1,600 years. That's the engine of the million-year memory.
So this stratified structure, it means that current surface chemical signals, like changes in carbon fluxes, they get transmitted into the deep ocean and are only mixed back to the surface over centuries to millennia.
That's the literal mechanism of the ocean's memory in action. We are storing chemical signals in the deep that won't fully resolve for dozens of human generations.
Okay, so let's synthesize this. The ocean's fundamental chemistry is acting as the planet's average history book. It's an integrated average of planetary events that span millions of years.
And in doing so, it provides this stable, constant ionic environment, the ancient chemical contract under which all marine life evolved.
Which brings us, of course, to the big question. If the ocean's stability is built over geological timescales, if it requires millions of years to achieve this balance, what are the consequences when humanity starts to disrupt the surface chemistry on timescales of decades?
It's a huge scale mismatch. We are forcing a system with a million-year memory to respond to a 100-year perturbation.
It's like we're pouring huge amounts of that fast money into the slow money trust fund.
Yeah.
And just expecting the balance to stay the same.
We're adding synthetic chemicals, we're dramatically increasing nitrogen and phosphorus runoff, and most alarmingly, we are acidifying the surface ocean with co-Euro at rates hundreds of times faster than any natural geological process.
And all marine life evolved, assuming this constancy. Their entire cellular machinery, their ability to form shells, it's all predicated on those constant proportions and a certain pH.
We are testing the very limits of that ancient stability. We're changing the rules of the chemical contract at warp speed.
The risk is just profound. We always assumed the ocean was too big to fail.
But its resilience is built on patience and time, not on instantaneous speed. We are, frankly, running an uncontrolled experiment with consequences that are guaranteed to play out over centuries.
And that's the thought we have to leave you with. The ocean, though it's vast, may have very strict limits to its buffering capacity when it's faced with such rapid change. The consequences of altering its ancient chemical balance will play out over periods far, far exceeding human generations.
The carbon we pump in today is being written into a memory archive that lasts for centuries. We are programming the future of the planet's chemistry.
That covers 4.
Oh.
Ready for the next one? Let's head to fact 3. Welcome back. We are moving right along in our countdown. Let's dive into fact number 3. Today, we are sinking deep, 3 or 4 kilometers down into the abyssal zone to explore chemosynthetic ecosystems.
And some of the most extreme biochemistry on the planet.
Absolutely. If you think the rules of biology are, all written by the sun, get ready for a fundamental rewrite. This is the story of life powered purely by geology.
It completely shatters that solar dependence model. We're talking about environments with crushing pressure and permanent total darkness.
And yet, somehow they support these dense, complex biospheres.
The paradox is just so stark. But the answer is, well, it's revolutionary.
It really is. So our mission here is to unpack the how. How do the physics and the chemistry actually allow life to thrive at temperatures near 400 degrees Celsius?
And under hundreds of atmospheres of pressure, it's incredible.
And then we have to look at the bigger picture, the profound implications this has for what we even consider life and where we should be looking for it.
These vent systems show that energy from Earth's interior is a totally viable alternative to the sun. It's a completely independent biosphere on our own planet.
Okay, let's start with the engine itself, the volcanic engine. Where exactly are these biological power plants?
You find them along the major seams of the Earth. So think mid-ocean ridges, back arc basins. Specifically, we call them hydrothermal vents.
And it all starts with a kind of planetary plumbing system, right?
It's exactly that. It's like a closed-loop geothermal system. Seawater seeps down, sometimes for kilometers, into the oceanic crust through all these fissures and cracks.
And as it goes down, it gets heated by magma.
Superheated. And this process isn't just warming the water, it's cooking it under immense pressure. It forces these intense chemical reactions with the rock around it, stripping out oxygen, loading it up with minerals.
Before it gets shot back out onto the ocean floor.
Precisely.
And when it discharges, the conditions are just mind-bending. Let's talk specifics. Temperature, for instance.
The vent fluids can exit at anywhere from 350 to 400 degrees Celsius.
Which is astounding. I mean, at the surface, that would just instantly flash into steam.
Superheated steam, yeah. But down there, we're at depths where the pressure is hundreds of atmospheres. It increases about 1 atmosphere every 10 meters you go down.
So that immense force is literally compressing the water molecules.
It's forcing the water to remain liquid, even at temperatures that should, by all rights, vaporize it instantly.
And that creates this incredibly unstable, high-energy environment.
It's a physical state we just don't encounter up here. And it's critical for a couple of reasons. One, it keeps the water liquid, which is essential for life.
And 2,
the high pressure allows that superheated water to dissolve and leach out way more chemical content from the rocks it's flowing through.
okay, so the water that comes out isn't just hot, it's chemically transformed. Our sources say it's enriched in reduced chemicals, things like hydrogen sulfide, methane.
Right, hydrogen gas, reduced metals.
For those of us who aren't chemists, what does reduced actually mean here? Why is that the key?
It just means they're electron rich. Think of them as tiny charged up energy batteries. They're highly reactive.
Okay.
Up here on the surface, most of life runs on stable oxidized compounds, carbon dioxide, water. Down there, the fluids have been stripped of oxygen and loaded with these unstable high-energy compounds.
And at concentrations way, way higher than the surrounding seawater.
Orders of magnitude higher. It's a chemical soup.
So you have these volatile 400-degree fluids just blasting into frigid 2-degree ambient seawater. That moment of mixing must be incredibly dynamic.
It is the defining feature of the entire ecosystem. That collision zone creates a massive, sudden temperature drop, of course.
But more importantly,
It establishes a sudden, steep redox gradient.
okay, hold on. What exactly is a redox gradient in this context? Why is that the fuel?
Redox is short for reduction oxidation. It just describes the potential for electrons to be transferred. A steep gradient means there's a huge immediate difference in that potential between the two fluids.
So the hot vent water is desperate to get away its electrons.
Desperate. And the cold, oxygenated bottom water is just as desperate to take them.
And life has just positioned itself right in the middle of that chemical tug-of-war.
Exactly. That sudden, violent urge for the chemicals to balance themselves out, that electron transfer, that is the energy source. The microbes just built a way to stand in the middle and harvest the energy that's released.
And this is where the biology becomes so fascinating. Surface life has photosynthesis, sunlight. But down here, no light. So the primary production is all based on chemosynthesis.
Metabolic alchemy. It's alchemy fueled by geothermal heat.
The foundation of this entire food web, then, rests on these chemolithoautotrophic microorganisms. Is that right?
Chemolithoautotrophic. You got it. They're the primary producers. They're the equivalent of the plants and the phytoplankton on the surface.
But instead of sunlight, they're capturing energy by oxidizing those reduced chemicals we talked about.
Hydrogen sulfide, ferrous iron, methane. They're essentially running a controlled slow-motion combustion of these geological products.
And they couple that reaction to oxidants they pull from the cold water. Oxygen, mostly.
Mostly oxygen, but they can also use nitrate or even sulfate if oxygen is scarce. They're very adaptable. The energy released from that transfer is then captured.
And once that energy is captured, the outcome is the same fundamental process for all life. They use it to fix inorganic carbon corridor into organic matter.
They are literally building sugars and proteins out of toxic chemicals and planetary heat.
What's so fascinating is the sophistication of their toolkit. I mean, this isn't just survival, this is optimization. The research shows a whole diversity of different carbon fixation pathways.
Right, they have multiple ways to do the same essential job, which points to a lot of complexity.
I've heard of the Kelvin-Benson cycle. That's the common one in plants.
Yeah.
Are these other pathways just running that one backward, or is the chemistry different?
Oh, they're fundamentally different. It shows deep, independent evolutionary history. We see the reductive tricarboxylic acid cycle, the RTCA cycle, which, yes, effectively runs the normal TCA cycle in reverse to build carbon instead of burn it. But we also see something called the acetyl-CoA, or Wood-Ljungdahl pathway.
That one sounds dense, but it's really central to how they succeed down there, isn't it?
It's their deep-sea superpower. It's often cited as the most energetically efficient, non-photosynthetic pathway for fixing carbon known to science.
More efficient? How so?
It lets them synthesize organic matter very quickly, using extremely simple building blocks like hydrogen and cocoa, and it does it with minimal energy loss. It's an adaptation for thriving in these really challenging high-pressure environments.
And to do this, they rely on specialized enzymes. The source mentions formate dehydrogenase and carbonic anhydrase. These sound like a big deal.
They're essential. Think of them as industrial equipment at the molecular level. Carbonic anhydrase, for instance, dramatically speeds up how CoA dissolves and gets ready to enter the cycle. This isn't primitive life, it's highly specialized.
And these microbes, they form these thick, expansive biofilms on the vent chimneys. They're the foundation.
They are the foundation for an entire, thriving, visible ecosystem.
That's the visual punch, right? You expect to see barren mud, but instead you find these dense communities of animals.
Huge animals. Giant, bright red and white tube worms, foot-long clams, strange blind crustaceans. It's a massive oasis of life clustered just around this chemical outflow.
The giant tube worm, Riftia, is the real aha moment. It just reveals this total commitment to symbiosis. We're talking about an animal that, as an adult, has no digestive tract.
Nothing. No mouth, no gut, no anus. It has zero ability to eat physical foods.
It's outsourced digestion entirely.
The whole concept. The tube worm is just a highly sophisticated delivery vessel for its internal partners, these sulfide oxidizing bacteria that live inside a special organ.
The trophosome.
The trophosome. The bacteria make the food, and the worm's only job is to transport the ingredients to them.
And that delivery process is a physiological marvel. The worm has to transport two things that are incredibly reactive with each other. Sulfide, which is the food, and oxygen, the reactant.
And it has to do it without letting them meet and react inside its own body, which would be toxic.
How does it manage that?
Specialized blood pigments. They're way more efficient than our hemoglobin. They're engineered to bind both the oxygen and the toxic hydrogen sulfide at the same time, but on different sites on the molecule.
So it keeps them separated.
Perfectly separated until they're delivered safely to the bacteria. The bacteria then do their chemosynthesis, make the sugars, and the worm just absorbs its share. It's an incredible solution.
A high-pressure, non-reactive chemical delivery service. It's a masterstroke.
And this activity isn't just localized. These vent systems themselves are critical hubs of geochemical flux for the entire deep ocean. They pump massive amounts of heat and elements like iron, manganese, and helium into the global system.
And the microbes are mediating those fluxes. They're driving the reactions that make the metal sulfides precipitate out of the water. That's what builds the towering chimneys, the black smokers we always see pictures of.
Life is literally building the geology of its own habitat.
So we've established this incredible sun-independent system, but why should you, our listener, really care about life 4 kilometers down?
Because it connects us directly to the biggest questions there are. First, these metabolic pathways, this chemosynthesis, they give us a direct window into what life might have looked like on early Earth.
Right, before the atmosphere was full of oxygen, or before photosynthesis was widespread.
It shows how life could have gotten a foothold. And second, the cosmic implications are just profound. Because this life is sustained solely by geological energy, it provides the essential template for what life could look like on other worlds.
We're talking about the icy moons, Europa and Enceladus.
Exactly. Places with subsurface oceans kept liquid by internal heat from tidal forces or radioactive decay. They're way outside the traditional habitable zone where you'd need sunlight.
But they have the key ingredients: internal heat, water, and rock to react with.
The existence of life at these vents on Earth tells us that life can and will exploit that kind of geological energy source. It forces us to broaden our definition of a habitable world beyond just a planet's surface.
It just illustrates the sheer breadth of conditions life can handle. Permanent darkness, near boiling temperatures, hundreds of atmospheres of pressure. Biology is relentless. It will find a way.
The deep ocean is not a wasteland. It's a massive, sun-independent biosphere built brick by chemical brick on the power of planetary geology.
Which leaves us with a truly provocative final thought. Since life on Earth can thrive using chemical energy from a planet's interior, and the building blocks for that, water, rock, heat, are common across rocky planets and icy moons. Is it possible that the most common form of life in the universe is actually subterranean and chemosynthetic? Is surface photosynthetic life like us the real anomaly?
That question fundamentally changes the entire search for life out there.
That covers 3. Ready for the next one? Let's head to fact 2. Welcome back. We are moving right along in our countdown. Let's dive into fact number 2. Today, we're drilling down into something that, well, fundamentally alters how you picture our own planet. When you look at Earth from space, you see that massive blue ocean, right, covering over 70% of the globe.
Of course, it's the defining feature.
But what if I told you that familiar ocean is? It's just the visible bit, the very top layer of a vast, planet-wide water system.
The visible interface.
Exactly. A system that plunges hundreds, maybe thousands of kilometers deep into the Earth's interior. We're talking about a truly vertical hydrosphere.
And that verticality is the key insight. It's something modern science is really only just beginning to quantify.
So the water cycle we learned in school is just scratching the surface.
Literally, yes. That whole cycle of evaporation, condensation, precipitation, that's the surface loop. What we're talking about here is a deeper, far more powerful system.
Earth's vertical hydrosphere.
Right, and this one exchanges mass water, specifically from the atmosphere, all the way down into the deep mantle.
And crucially, this operates on geological timescales. This isn't something you measure in years or decades.
Not at all. The speed of the cycle, it varies wildly. You have the relatively quick release of water from a volcano.
Which you could measure over a few days.
And then you contrast that with these immense slow processes like whole mantle convection cycles. Those take hundreds of millions of years to move material just once.
Wow.
And it's the sheer duration of that deep cycle that we think stabilizes Earth's long-term environment.
Okay, let's just try to unpack the scale here. If our oceans are just the visible part, how much water are we actually talking about hidden beneath our feet? What's the size of this deep reservoir?
The scale is shocking. Our sources use a great analogy for this. They say to think of the surface ocean as the ground floor of a building.
Okay.
That ground floor alone holds about 1.4 times 10 to the 21st kilograms of water.
Which is a number so big, it's meaningless.
It's 1.4 septillion kilograms. It's just, yeah, it's an abstract concept at that point. Now, if the surface is the ground floor, the models suggest that the deep mantle basement, this reservoir, hundreds of kilometers down, could contain an amount of water comparable to, or even several times greater than what we see on the surface.
Wait, several times?
Yeah.
So you're saying there could be 2, 3, maybe 4 Pacific Oceans worth of water hidden inside the planet.
That's what the models point to. Yes.
That's just, it changes everything. The idea of Earth being a wet planet isn't just about the blue surface. We are wet through and through.
Deeply wet.
But hang on, if you go that deep, the temperature and pressure are enormous. How can the mantle, which is solid rock, hold that much water? It can't be liquid, can it?
No, absolutely not. If it were liquid, the seismic effects would be catastrophic. The planet would be incredibly unstable.
So how?
The water is chemically stored. Under that intense heat and pressure, the H0 molecule, well, it breaks apart. Its components, hydrogen and oxygen, get incorporated directly into the crystal structure of high-pressure minerals.
So it's not a hidden sea. It's more like the rock itself becomes damp on a molecular level.
That's a perfect way to think of it. It's stored as hydroxyl groups, which is the ion ORO. So it's less like water and more like a pervasive dampness locked deep within the mineral lattice itself.
And is there a specific place this happens?
There is. The key location for this storage seems to be the mantle transition zone.
Which is how deep?
It sits roughly between 400 and 660 kilometers down.
That's a very specific zone. Why there?
Because of a mineral that dominates at that depth. Ringwoodite.
The ringwoodite.
Ringwoodite is incredibly efficient at soaking up these hydroxyl groups. It's like it has these perfect little slots in its crystalline structure for locking in OO ions under exactly those pressure conditions. The transition zone acts as the planet's largest deep sponge.
A giant sponge layer deep inside the Earth. That is a powerful image. What about the history? Where did all this water come from in the first place?
Well, a lot of Earth's initial water was actually trapped in a primordial magma ocean when the planet was first forming.
So it was baked in from the start.
Exactly. As the mantle solidified, the water was just entrapped deep within. The ocean we see today was formed later, released through volcanic degassing over billions of years, mostly during the Hadean and Archean eons.
So our oceans came from the inside out. The planet exhaled them.
Largely, yes. Which brings us back to the current cycle. We now have a stable planet with plate tectonics, and that is the engine driving this whole thing.
The geological conveyor belt.
Right. And it has two key processes: ingassing, which is water going in, and outgassing, which is water coming back out.
Let's try to visualize this. Let's follow a single water molecule on its journey.
A very long journey.
Okay, so imagine our molecule starts in the Pacific Ocean. It gets trapped in the oceanic crust, maybe inside a hydrated mineral called serpentine.
Which forms when seawater reacts with hot rock at mid-ocean ridges. Very common.
Then the tectonic plate starts to descend at a subduction zone, where one plate slides under another. That's the moment of ingassing.
Right, and that subduction process drags that water molecule hundreds of kilometers deep. The temperature and pressure just skyrocket.
What happens to the serpentine?
By the time it hits, say, 400 or 500 kilometers down, the serpentine structure breaks down and it releases the water.
Which then gets soaked up by the ringwoodite.
Exactly. It rushes to bind into that ringwoodite structure in the transition zone we just talked about.
And how long does it stay there?
Now, this is where time starts to lose all meaning. It could remain as a hydroxyl group in that ringwoodite, just creeping along with the mantle's convection currents for maybe 100 million years.
100 million years. That's longer than the dinosaurs ruled the Earth.
It's an almost incomprehensible amount of time for a single molecule to be trapped inside solid rock.
How does it ever get out?
The escape is triggered by melting. Eons later, that bit of mantle rock, now slightly changed, might start to rise in a buoyant plume. As it rises, the pressure drops.
And that causes it to melt.
Partially melt, yes. And that chemically locked-in water escapes the crystal and partitions back into the liquid magma. The magma rises quickly and boom! That water molecule finally erupts as steam from a volcano, maybe in Iceland or along the mid-Atlantic ridge.
And that's outgassing.
That is the outgassing process. Every plume of volcanic steam is the deep earth exhaling a tiny bit of its ancient water.
So what's the balance today? Are we breathing in as much as we're breathing out?
Well, we can measure the outgassing rates. They're estimated between 0.4 and 1.2 times 10 to the 11 kilograms per year.
Which sounds like a lot.
It is a lot, enough to fill a big lake every year. But compared to the whole ocean, it's a tiny drip. Now, the inflow, the ingassing, is driven by subduction, constantly dragging water back down.
And when you put those two numbers together in the models,
This is where it gets really fascinating. The models and the geochemical evidence, they strongly suggest that the net balance may currently favor ingassing.
so more is going down than is coming up.
Slightly more, yes. It implies that under modern tectonic conditions, the deep mantle basement, that sponge layer, might actually be slowly refilling.
We are slowly sequestering our own surface waters back into the deep earth.
Over vast timescales, yes.
Okay, before we get into the huge implications of that,
Yeah.
there's the other source, space. Comets, asteroids, how do they fit in?
Right, the exogenous delivery. And that's where the cool science of isotopic tracking comes in. We can tell where water came from by measuring its ratio of deuterium, a heavy isotope of hydrogen to normal hydrogen.
The DDH ratio, it's like a fingerprint.
A very reliable one. Water that formed way out in the cold solar system, like in comets, tends to have a higher DH ratio than water from closer to the sun, or water that was trapped deep inside a hot forming planet.
So you compare the fingerprint of our oceans to the fingerprint of comets.
And we've found some matches. Measurements from certain comets, like 46P Virtanen, have shown isotopic ratios that are a very close match for Earth's oceans.
So that confirms they delivered at least some of our water.
Absolutely. They delivered a substantial, maybe even critical fraction, but the consensus, when you factor in the deep cycle, is still that internal degassing was the dominant source, just augmented by these external deliveries. The internal cycle is the primary long-term manager.
So the mantle isn't just a passive storage tank. It's an active manager. What is all that water doing down there?
It's acting like a planetary lubricant. It's anything but inert. Even as hydroxyl groups, it critically influences the melting behavior and the viscosity of the mantle rock.
How so?
Introducing those hydroxyl groups into the mineral lattice effectively weakens the rock. It makes it more pliable, less stiff.
So if the mantle were to dry out, it would become too rigid and plate tectonics could slow down or even stop.
Precisely. This is a leading theory for why Earth has active plate tectonics, and planets like Mars or Venus, which seem to have dried out, don't. That deep water is essential for the mechanism of plate tectonics to even work.
That is an incredible feedback loop.
Yeah.
The water going down helps the conveyor belt keep running.
And the running conveyor belt then helps regulate the entire surface environment.
Yeah.
That deep coupling modulates volcanism and subduction, which in turn regulates the exchange of heat and volatiles like CoO. This whole loop is what maintains a stable surface temperature and ensures the persistence of liquid water on the surface over billions of years.
It's the ultimate planetary thermostat. Our oceans are stable because of this huge, slow-moving internal machine.
Right. It's why 4 billion years later, we still have continents, active plates, and liquid water all at the same time.
Which brings us to the big philosophical question. What does this mean for the long-term future, if that net imbalance is real?
If subduction continues to draw water into the mantle faster than volcanism releases it,
Will Earth's surface oceans eventually disappear, swallowed by the mantle?
it's the logical, though extremely slow, consequence of sustained net engassing. If the surface ocean shrinks significantly, you lose that crucial buffer for the climate. The whole system could collapse.
And surface water is everything for habitability.
The single most important component.
This is the real aha moment. We need the deep cycle to keep the planet alive tectonically, but we absolutely need the surface water to sustain life. It's a Goldilocks balance.
A balance that's been held for 4 billion years. The key question is about the optimal distribution of that water. Too much in one place is bad.
Too much in the mantle, and we dry out.
But there are also theories that too much water on the surface could be a problem. If the surface were too flooded, the sheer weight of all that water could potentially lead to a stagnant lid planet where plate tectonics stops because the crust is too weak and saturated to subduct properly, geologically dead, like Venus.
So Earth has somehow managed to keep just enough on top and just enough below for 4 billion years.
And understanding the exact mechanism that maintains that balance, the tipping point between ingassing and outgassing, that's one of the biggest questions in Earth science today.
So the core takeaway here is that the ocean we see, it isn't an isolated feature. It's the visible tip of this dynamic vertical system, reaching from the sky all the way down to that critical ringwoodite sponge layer.
A massive planetary system that defines Earth's habitability.
Which leaves us with a final provocative thought to mull over. Is Earth's surface ocean truly permanent? Or is it just a transient feature in a much longer, slower, deep Earth cycle that we are only beginning to comprehend? That covers 2. Ready for the next one? Let's head to fact 1.
We have finally reached it. The most magnificent revelation on our list. Fact number 1.
It really is. I mean, this is the one. It's more than just another fact. It's the idea that ties everything else together.
Everything we've discussed, from the deep sound channel to the global conveyor belt.
Exactly. This is the fact that dissolves the line between, Earth science and just science. It's cosmology, it's physics. For you, the listener, this is the moment where our planet stops being an isolated blue marble and becomes this fully integrated piece of the cosmos.
That's the core of this deep dive, isn't it? We're taking on this huge concept. The ocean isn't just a feature on Earth, it's a cosmic artifact. It's what you get when you let the laws of physics play out over billions of years of stellar evolution and planetary formation.
And that's our mission today. We are going to trace the story of a single drop of seawater all the way back.
All the way back to the beginning.
To the very beginning. We want to show how this enormous body of water connects our planet to the entire universe and why it's our ultimate reference point for habitability, for where else life might be hiding.
It's a huge shift in perspective. So let's frame the question for you, our listener, as we get started. Just think about this. What if the water you swim in, the water you drink, is fundamentally the same cosmic recipe that defines the potential for life across the entire galaxy?
Let's get into it.
Okay, let's start at the most basic level. The ingredients. H-arrow. 2 atoms of hydrogen, 1 atom of oxygen. And what's so incredible is that these 2 elements have, completely different and spectacular origin stories.
Dramatically different.
Yeah.
And they're separated by billions of years of cosmic history.
Yeah.
That simple formula, HAO, It sort of hides this incredible story. It's a union between the oldest matter in the universe and matter forged in, well, the most violent events imaginable.
So let's start with the oldest part, the two H's. The hydrogen, you said these are relics. Just how old are we talking?
We are talking 13.8 billion years old. The hydrogen atoms in every single molecule of water on Earth were created in the first 3 minutes after the Big Bang.
That's a statement that feels like it should be in a movie. The water in my glass is made of stuff from the literal dawn of time.
It's primordial. In those first moments, the universe wasn't stars and galaxies. It was this incredibly hot, dense soup of particles, a plasma.
Too hot for atoms to even exist.
Way too hot. But as the universe expanded, it cooled. And in this very brief window, from about 1 second to 3 minutes in, it was cool enough for protons and neutrons to stick together.
And that process is Big Bang nucleosynthesis.
Right. And the universe expanded and cooled so fast that it really only had time to make the lightest elements. It made a ton of hydrogen, about 75% of all the normal matter, and a good amount of helium, about 24%.
And just a tiny bit of other things, like lithium.
Tiny, tiny traces. Everything heavier, every single other element on the periodic table had to wait. It had to be made somewhere else, much, much later.
So the hydrogen in our oceans basically just survived. It's been floating around the universe since the beginning, waiting for a home.
That's a perfect way to put it. It's the foundational block. Now, contrast that really ancient, almost quiet origin with the story of the oxygen atom, the O in HO.
Yeah.
That element is pure stellar drama.
It's a completely different production. This is where we get into the stellar furnaces.
Exactly. For oxygen, you need immense temperatures and pressures. The kind of conditions you only find deep inside the cores of very massive stars. Stars, say, 8 times the mass of our sun or more.
And our sun can't do that.
The sun is a little too small. It's happily fusing hydrogen into helium, and it will for billions more years. But in these giant stars, as they age, they run out of hydrogen in their core. The core collapses, heats up, and starts fusing helium into carbon.
And then it keeps going up the chain.
It keeps going. After carbon, it can fuse carbon with another helium to produce oxygen. Each step requires even more heat and pressure. So you end up with these layers inside the star, like an onion, fusing heavier and heavier elements.
So, if I have this right, hydrogen is the child of the Big Bang, and oxygen is the child of a giant long-dead star.
And that gives us this crucial insight. Astronomers have a term for everything heavier than hydrogen and helium. They just call them metals.
Right. So, to an astronomer, the oxygen we breathe is a metal.
It's a metal. And all these metals, the oxygen in water, the carbon in our bodies, the iron in our blood, they are literally the ashes of previous generations of stars. Our solar system is what we call a second or even third generation system. It's built from recycled material.
But, okay, there's a problem here. If the oxygen is made deep in the core of a star, how does it get out? How does it get from there, across light years of empty space, into the cloud of gas that eventually formed our planet?
That is the supernova delivery system. It is absolutely essential. Once a massive star builds up a core of iron, it's game over.
Because fusing iron doesn't release energy.
It actually consumes energy. So the furnace goes out, gravity wins, and the core collapses catastrophically. This collapse then rebounds in one of the most powerful explosions in the universe, a Type II supernova.
An explosion so bright it can outshine its entire galaxy for a few weeks.
For a short time, yes. And it's that incredible violence, that shockwave, that blasts all those heavy elements the star spent its life creating, including huge amounts of oxygen out into the interstellar medium.
It's a cosmic seeding event.
It is. Without the supernova, oxygen stays trapped. With the supernova, it enriches the galaxy, making it available for the next round of star and planet formation.
So these atoms, hydrogen from the beginning of time and oxygen from a stellar explosion, drifted through space for who knows how long, and eventually they get swept up into this huge molecular cloud.
The one that collapsed to form our solar system about 4.6 billion years ago. And now the story shifts. We go from the galactic scale down to the planetary scale, because the conditions right here determined how and where water could form.
This is where we get to the concept of the ice line.
The ice line, sometimes called the snow line, is a really critical concept. Imagine the young sun at the center of this huge spinning disk of gas and dust, the protoplanetary disk.
And it's hot near the center and cold farther out.
Very hot. And there's a distinct boundary. The ice line is the distance from the star where it's cold enough for water to condense into solid ice crystals.
And that's roughly where Jupiter is today, right? About 5 times the distance from the Earth to the Sun?
Around there, yes. Inside that line, it's too warm. Any water exists only as a vapor, a gas. But outside that line, it's cold enough for water to freeze onto dust grains. And this is so important because ice acts like a kind of cosmic glue.
It makes it easier for little bits of dust and rock to stick together and grow.
It dramatically speeds up the process. It helps explain why the giant planets like Jupiter and Saturn formed out there, but it also creates a puzzle for us.
Because Earth formed well inside the ice line, our neighborhood was the hot, dry inner part of the disk.
Exactly. So the primordial Earth, during its initial formation, was probably a very dry world. The material it was built from didn't have much water ice, which raises the big question, where did our oceans come from?
If it wasn't here to begin with, it had to be delivered later.
It had to be delivered later. And this is a huge area of research, but the consensus points to material that formed beyond the ice line, in the colder regions, being delivered to the inner solar system.
We're talking about icy asteroids and comets getting knocked out of their orbits and sent our way.
That's the leading theory. Things like C-type or carbonaceous asteroids, which are very rich in water and other volatile compounds. They formed out in the asteroid belt and beyond. And during the chaotic early days of the solar system, gravitational nudges from Jupiter and Saturn could have sent a barrage of these things flying inwards.
A period sometimes called the Late Heavy Bombardment.
Precisely, a time when the young Earth was being pummeled by these water-rich bodies. It's likely that this is how the vast majority of our planet's water arrived.
But wait, I remember there's a slight complication here, a bit of a scientific detective story. Don't comets have the wrong kind of water?
Ah, yes. You're talking about the D to H ratio.
The deuterium to hydrogen ratio. Explain that for us.
So deuterium is a heady isotope of hydrogen. It has a proton and a neutron in its nucleus, instead of just a proton. The ratio of this heavy hydrogen to normal hydrogen acts like a chemical fingerprint, and it varies depending on where in the solar system something formed.
Colder places have more of the heavy stuff.
Generally, yes. And when we look at most comets, especially those from the very distant Oort cloud, their D/H ratio is about twice as high as the water in Earth's oceans.
So if comets were the only delivery service, our oceans should have that same high D/H ratio, but they don't.
They don't. Which suggests that while comets probably contributed some water, they likely weren't the main source. This is what points the finger more strongly at those carbonaceous asteroids.
Because they formed closer in than the comets.
A bit closer, yeah. Closer to the ice line, but still beyond it. And when we've been able to measure samples from these asteroids, their D/H ratio is a much better match for Earth's oceans. So the picture is probably a mix, but with asteroids doing most of the heavy lifting.
So our ocean is an immigrant delivered by space rocks from the outer asteroid belt.
And that's the perfect lead-in to this visualization, this rewind time idea.
This is what I want you, the listener, to really sit with for a second. Picture yourself swimming in the ocean. Feel the water. Now, rewind time.
Follow those water molecules back. Back past human history, past the dinosaurs, back through the formation of the solid crust.
Back to the time of fiery impacts, when those asteroids delivered the water. Back further, to the protoplanetary disk, where that water was just ice on a dust grain orbiting the young sun.
Keep going. Rewind past the formation of the solar system itself. Follow the oxygen atom back across the galaxy to the heart of a giant star that exploded in a supernova.
And then follow the hydrogen atoms, all the way back, past the formation of the first stars and galaxies, back to the hot, dense fog of the first 3 minutes of the universe itself.
Every single swim you take is in water that connects you directly to the entire 13.8 billion year history of the cosmos. Our oceans aren't an afterthought. They are the grand, inevitable result of all of it.
Okay, so that sets the stage perfectly. We've got the ingredients from the Big Bang and from dying stars, and we've got the delivery system. But now we have to talk about Earth itself. Why was our planet able to hold on to this water and keep it liquid for billions of years?
Right, because getting the water is only step one. Keeping it is the real challenge. And it all comes down to a perfect combination of two things: mass and position.
Let's start with mass. Why was being the right size so important?
Gravity. If Earth had been smaller, say the size of Mars, its gravitational pull would have been too weak to hold on to a thick atmosphere over geologic time.
So the water would have just escaped into space.
A lot of it would have, yeah. Through a process called hydrodynamic escape. Lighter gases, like hydrogen that gets split from water by sunlight, can easily reach escape velocity on a small planet. Mars had oceans once, but it was too small to keep them. Earth was massive enough to hold on tight.
And then there's position, the famous Goldilocks zone.
The habitable zone. We are at that just right distance from the sun. Not too hot, not too cold,
It seems so simple, but the consequences are
They're
enormous.
everything. Look at our neighbors. Venus is only about 30% closer to the sun, but that was enough to trigger a runaway greenhouse effect.
Explain how that works. Water vapor is a greenhouse gas, right?
A very potent one. So, on early Venus, as the sun got a little brighter, the ocean started to evaporate more. More water vapor in the atmosphere trapped more heat, which caused more evaporation.
A vicious cycle.
A runaway feedback loop. Eventually, all the surface water boiled away into the atmosphere. Then, high up, ultraviolet radiation from the sun split the water molecules into hydrogen and oxygen. The light hydrogen escaped to space, and the oxygen reacted with the crust. Venus lost its water forever. Earth was just far enough away to avoid that fate.
We were on a razor's edge.
A planetary razor's edge, yes. So once the planet cooled down, that delivered water wasn't just on the surface, it got partitioned. Some went into the atmosphere, some formed the oceans, and a lot of it got incorporated into the planet's interior as it solidified.
So the initial oceans were probably fed by massive planet-wide volcanism, the planet essentially burping out the steam that was trapped in its molten rock.
A process called degassing. Absolutely, that's how you get the first surface oceans. But this is where we have to connect back to a fact we covered earlier, fact number 2, the deep water cycle.
The idea that the ocean we see is just the tip of the iceberg.
It's just the visible part of a hydrosphere that extends hundreds, maybe thousands of kilometers deep into the mantle. And the engine that drives the exchange between the surface and the deep Earth is plate tectonics.
The great recycler. So how does plate tectonics pull water down into the planet?
It starts at mid-ocean ridges, where new oceanic crust is formed. This crust is hot and dry at first, but as it moves away from the ridge and cools over millions of years, seawater seeps into it through cracks.
And this isn't just filling pores in the rock, it's a chemical reaction.
It's a fundamental chemical alteration of the rock itself. The water reacts with minerals in the mantle rock, like olivine, and forms new hydrated minerals. The most famous one is serpentine.
And in serpentine, the water isn't liquid Ichiro anymore.
No, it's chemically locked into the mineral's crystal structure as hydroxyl groups. It's called bound water. That oceanic crust might soak up a huge amount of water this way.
And then that entire slab of crust gets dragged back down into the mantle at a subduction zone.
Taking all of that bound water with it, it's a massive conveyor belt, transporting surface water deep into the planet's interior.
So where does it go once it's down there?
Well, as that slab goes deeper, it heats up, and those hydrated minerals become unstable and release the water. But the story doesn't end there. There are other minerals deeper in the mantle that are capable of holding onto that water, even under immense pressures.
This is where we get to the idea of a massive internal reservoir.
This is it. The key region is called the mantle transition zone, between about 400 and 660 kilometers down. The pressures there are so intense they change the crystal structure of olivine into new minerals. One is called wadsleyite, and deeper still is ringwoodite.
And ringwoodite is the key player here.
Ringwoodite can act like a sponge. It can incorporate a significant amount of water, up to 2.5% of its weight, into its crystal structure.
So we have a layer of spongy rock hundreds of kilometers beneath our feet. How much water are we talking about potentially?
The estimates are, frankly, staggering. Based on laboratory experiments and seismic evidence, it's plausible that the amount of water stored in the transition zone, mostly in ringwoodite, is equal to, or maybe even several times, the amount of water in all the surface oceans combined.
That's incredible. The ocean we see might be the small one.
It might just be the thin film on top. But this isn't just passive storage. This deep water cycle is an active, critical regulator of the entire planet. It creates a feedback loop.
How does water deep in the mantle affect us up here on the surface?
It fundamentally changes the properties of the rock. Even a tiny amount of water drastically lowers the melting point of mantle rock and makes it less viscous. It makes it flow more easily.
It's like a lubricant for the planet's engine.
That's a great analogy. It lubricates the asthenosphere, the layer the tectonic plates slide on. If the mantle were bone dry, it would be much stiffer. Plate tectonics as we know it might slow down or even stop altogether.
And without plate tectonics,
you lose the planet's long-term thermostat. Plate tectonics is crucial for regulating key errors in the atmosphere over millions of years. Subduction drags carbon down, and volcanism, which is enhanced by water, brings it back up. This cycle has kept Earth's climate stable enough for liquid water to persist for billions of years.
So the ocean, by allowing itself to be subducted, actually ensures its own long-term survival.
It's a beautiful self-regulating system. The surface ocean and the deep interior are locked in this symbiotic relationship. The ocean isn't just sitting on the geology, it is actively shaping it.
Okay, we've gone from the Big Bang to the deep mantle. Now we need to zoom in, all the way down to the molecule itself, H, Euro. Because it's the weird, unique physics of water that truly enables life and stabilizes our world.
We have to talk about quantum mechanics. I mean, that's really what it comes down to. All of water's bizarre and life-giving properties, the things that make it so different from other molecules of its size, they all stem from the shape of the molecule and something called hydrogen bonding.
Let's do a quick refresher on why HA is so strange.
It starts with its shape. The two hydrogen atoms are bonded to the oxygen at an angle, making it look a bit like Mickey Mouse's head. And oxygen is very electronegative, which means it's greedy for electrons.
It pulls the shared electrons closer to itself.
Right, which gives the oxygen side of the molecule a slight negative charge, and the hydrogen side a slight positive charge. It's a polar molecule.
A tiny magnet.
A tiny magnet. And because of that, the positive hydrogen end of one water molecule is strongly attracted to the negative oxygen end of another. That attraction is a hydrogen bond.
And these bonds are the secret sauce.
They are the secret to everything. They're much stronger than the forces between most other liquid molecules, and they cause the molecules to stick together tenaciously. This explains why water has such a high heat capacity.
This is the climate regulator we were talking about, the 1000x advantage.
That's the one. The ocean stores about 1,000 times more heat than the atmosphere for the same temperature change. To warm up water, you don't just have to make the molecules move faster. You first have to spend a huge amount of energy breaking all those sticky hydrogen bonds.
It acts like a giant thermal sponge soaking up heat.
It's the planet's heat battery, and right now it's absorbing over 90% of the extra heat that's being trapped by greenhouse gases. If it weren't for the ocean's heat capacity, the atmosphere would have warmed up catastrophically by now.
We are completely reliant on this single physical property of water.
We are. And it's not just heat capacity, it's also latent heat. The energy needed to change phase, like from liquid to gas. Evaporation from the ocean surface carries a tremendous amount of heat energy high into the atmosphere, which is what powers weather systems and distributes heat around the globe.
But let's get to the weirdest property of all, the density anomaly, the fact that ice floats.
This is maybe the best example of quantum physics dictating global habitability. As you cool liquid water, it gets denser and denser, like most things, but only down to about 4 degrees Celsius.
Below that, it starts to get less dense again. Why?
It's those hydrogen bonds again. As the molecules slow down, the hydrogen bonds start to lock them into a very specific, open, crystalline structure, a hexagonal lattice.
They're building a scaffold.
An open scaffold. In that rigid ice structure, the molecules are actually farther apart on average than they are in the cold, jumbled liquid state. It takes up more space, so it's less dense, and that's why it floats.
And the consequence of that is profound. If ice sank, oceans and lakes would freeze from the bottom up.
They'd become solid blocks of ice in winter. Life would have an incredibly hard time surviving. The fact that ice floats creates an insulating layer on top, protecting the liquid water below. It's a simple quirk of physics. It's a prerequisite for complex aquatic life.
And that density behavior also drives deep ocean circulation, right?
Absolutely. In the polar regions, as surface water cools and gets saltier from ice formation, it becomes the densest water on the planet.
Denser than the water beneath it.
Much denser. And so it sinks. It plunges thousands of meters to the abyss, kicking off the formation of the deep water masses that drive the global thermohaline circulation.
This is the direct link back to fact number 7, the ocean's global memory, the conveyor belt.
It's the engine of the conveyor belt. And that engine is powered by the quantum mechanical behavior of the water molecule. Change the hydrogen bond slightly, and that entire planetary system of heat distribution grinds to a halt.
And beyond the physics, water is also the master chemical regulator.
It's the planet's buffer. This brings us back to fact number 4, the ocean as a chemical reservoir. It controls atmospheric heat aero over geological time through a series of chemical reactions.
The carbonate buffer system.
Exactly. When car Euro dissolves in seawater, it forms carbonic acid, which then releases hydrogen ions and becomes bicarbonate and carbonate ions. The ocean has a huge reserve of these carbonate ions.
And that's what keeps the pH stable.
That's the buffer. If the ocean gets a bit too acidic, those carbonate ions mop up the excess hydrogen ions. If it gets too basic, bicarbonate releases some. It's this elegant chemical equilibrium that has kept ocean pH in a narrow, life-friendly range for hundreds of millions of years.
A stability that also relies on life itself.
Critically, Marine organisms like phytoplankton build shells out of calcium carbonate. When they die, they sink, taking that carbon with them to the seafloor. It's a biological pump that constantly removes carbon from the surface system. It's all interconnected.
The physics, the chemistry, the biology, all stemming from the properties of that one single molecule.
It really is the masterpiece of planetary engineering.
Which brings us to the final and maybe the most awe-inspiring implication of all. If these laws of physics and chemistry are universal, then the ocean isn't just special to Earth, it's a universal template for life.
This is the shift in thinking. We have to move away from seeing Earth as a one-off miracle and start seeing it as a successful example of a process that could be widespread. The primary ingredient, water, is everywhere.
It's the third most abundant molecule in the universe, after hydrogen gas and carbon monoxide. We see its signature in interstellar clouds, in the disks around new stars.
All over the place. And now we're finding that ocean worlds might be common, even in our own solar system. And they're turning our ideas about habitable zones upside down.
We're talking about moons like Jupiter's Europa and Saturn's Enceladus.
Exactly. These moons are far outside the traditional Goldilocks zone, where it should be far too cold for liquid water. But they have an alternative heat source.
Tidal heating.
Tidal heating. The immense gravity of their parent planets, Jupiter and Saturn, constantly squeezes and stretches them. This friction generates a huge amount of heat in their rocky cores, enough to maintain vast, liquid water oceans hidden beneath their icy shells.
And we've seen proof of this, haven't we? The geysers on Enceladus.
We have. The Cassini spacecraft flew right through plumes of water vapor and ice crystals erupting from cracks in Enceladus's south pole, and it analyzed them. It found not just water, but salt, silica dust, and complex organic molecules.
Which means that water is in contact with a hot, rocky seafloor. It's a hydrothermal system.
It's direct evidence for a subsurface ocean with active chemistry. It suggests that these ocean worlds could be common throughout the galaxy, dramatically expanding the number of places where life might exist.
And this connects us directly back to fact number 3, the chemosynthetic life in our own deep oceans.
This is the template. If you're looking for life on a world encased in kilometers of ice, sunlight is irrelevant. You need an energy source that doesn't depend on a star. And our own hydrothermal vents prove that such a thing is possible.
Because they're powered by geochemical energy from the Earth's interior.
Let's walk through that link because it's the strongest we have in astrobiology. At Earth's ends, cold seawater seeps into the crust, gets superheated, and reacts with the rock.
A process called serpentinization.
Right, and that reaction creates a fluid that's rich in chemicals like hydrogen sulfide and, most importantly, molecular hydrogen. When that hot fluid erupts and mixes with the cold ocean water, it creates a powerful chemical energy gradient.
And the microbes at the bottom of the food chain harness that energy.
They eat the hydrogen gas and other chemicals to create their own food. They are completely 100% independent of the sun. They're living off the heat of the planet itself.
So since we expect the same kind of planetary heating on a moon like Europa, our vents provide proof of concept. They show that life could arise and thrive in a dark, high-pressure, subsurface ocean elsewhere.
The ocean, therefore, might be the standard cradle for life in the universe. It provides the liquid medium, the chemical transport, the thermal stability, and a potential geochemical engine.
And this all leads to the biggest question of all, the question of predictability. If the laws of physics are the same everywhere, and the ingredients are common, is life itself a predictable outcome?
Is it an inevitable consequence of complex water-carbon chemistry? If you have a stable, liquid water ocean on a rocky world for 1 billion years, does life just happen? That's the great debate.
And if we do find life on Europa, what will it look like? Will it be familiar?
That's the next level of the question. Will it use the same biochemistry, DNA and RNA, the same amino acids? If it does, it might suggest that there's a single, universal chemical path that life tends to follow.
Or will it be something truly alien?
A completely separate second genesis, a form of life that solved the same problems of replication and metabolism, but with a totally different chemical toolkit. Finding that would be, well, arguably the greatest discovery in human history.
And the key to answering any of those questions lies in understanding these ocean worlds.
The ocean is the stage. It's a link connecting our planet's very specific history all the way back to the Big Bang and all the way forward to the search for life across the cosmos. It's the one grand unifying narrative.
We have completed an extraordinary journey, tracing the origins of our blue planet's most defining feature, from subatomic components forged in deep space to its role as a cosmic template for life.
It really is astonishing when you put it all together. The ocean isn't just a big body of water, it's a library of cosmic history. It's universal physics made manifest right here, defining our world and enabling our own existence.
And that concludes our countdown of the 10 most extraordinary facts about the ocean. We started this whole series by looking at the big picture, the planetary scale, and we've ended up here at the universal constants that make it all possible.
Let's just do a quick recap of this entire journey from 10 all the way down to 1 to remind everyone of the sheer scope of what we've explored.
We started with fact 10. The ocean is a single planet-spanning fluid shell, this continuous body of water shaped by the spin of our planet.
We moved to fact 9. The ocean dominates Earth's living volume, providing more than 99% of the space where life can exist.
We explored fact 8. The deep ocean is a high-pressure, cold, planet-scale abyss, a realm of crushing pressure and eternal, freezing darkness.
We revealed fact 7. The ocean has a global thermohaline memory, that slow, deep conveyor belt storing the memory of past climates for 1,000 years.
We identified fact 6. The Southern Ocean is a global heat and carbon gatekeeper, the critical window where the deep ocean breathes and regulates our climate.
We discovered fact 5. The deep sound channel lets the ocean hear across basins, that amazing acoustic waveguide that carries the sounds of whales and volcanoes across entire oceans.
We analyzed fact 4. The ocean is a planet-scale chemical reservoir with million-year memory, with its chemical composition telling a million-year story of the continents.
We celebrated fact 3. The deep ocean hosts chemosynthetic ecosystems and extreme biochemistry, proving that life can thrive without the sun, powered by the planet's own inner fire.
We traced fact 2. Earth's ocean is part of a deep, planet-wide water cycle extending into the mantle, showing that the ocean we see is just the surface in a much larger planetary water system.
And finally today, we grasped fact 1. The ocean links Earth to cosmic and planetary context through universal physics, connecting every drop of water on our planet to the Big Bang, to dying stars, and to the search for life in the universe.
Thank you for joining us for this entire extraordinary journey. We hope this deep dive has given you, the learner, a profound new appreciation for the water that defines our planet and potentially the cosmos beyond. If you want to keep exploring these concepts and stay well informed, make sure you subscribe to the deep dive.
Thanks for listening to the Extraordinary 10 podcast.